the profound question of whether we are truly alone in this boundless universe, or if there might be intelligent life out there, waiting to be discovered, is a whisper that has echoed through human consciousness for as long as we have gazed up at the night sky. It's a thought that can feel both incredibly vast and strangely intimate, touching on our deepest hopes and our most profound curiosities. Imagine, for a moment, the sheer, unimaginable scale of the cosmos. Think of the countless galaxies, each a swirling island of billions of stars, and then try to comprehend how many planets might orbit just one of those stars. The numbers quickly become so immense, so mind-boggling, that our human minds struggle to fully grasp them. And yet, within that immensity, the question persists: are we, on our small, blue planet, the only sparks of conscious thought, the only ones capable of wondering about it all? Perhaps, as we ponder this, a subtle shift occurs within you, a sense of perspective. Perhaps our daily worries, our immediate concerns, begin to recede, becoming tiny specks against the backdrop of this cosmic inquiry. It's a humbling thought, isn't it, to consider that we might be just one tiny part of a much grander, much more intricate tapestry of life? The very idea of advanced civilizations often conjures images from stories we've heard, visions of beings far beyond our current understanding. Could they be hiding from us, observing from a distance, like careful gardeners watching a delicate sapling grow? Or, in some of our more anxious imaginings, might they be preparing for something entirely different, something that could impact our world in ways we can only speculate about? These thoughts are not meant to stir unease, but rather to gently invite your mind to stretch its boundaries, to consider possibilities that lie far beyond the familiar. It's like standing at the edge of a vast, tranquil ocean and wondering what marvelous creatures swim in its deepest, darkest parts, unseen and unknown. Unseen and then there's an even more intriguing whisper, a quieter, perhaps more profound thought that arises from the very bedrock of scientific speculation. What if the key to unlocking the deepest secrets of the universe, the very fabric of reality itself, lies not with life as we know it, based on carbon, water, and intricate organic chemistry, but with something entirely different? What if the universe's profound truths are held within the existence of silicon-based life? Imagine, for a moment, a form of life built upon the very element that forms the bedrock of our planet's crust, the raw material of rocks and sand. Silicon, with its atomic structure remarkably similar to carbon, possesses the potential to form complex, stable chains and networks, much like the carbon backbones of our own biological molecules. While it exists abundantly in the universe, the conditions for silicon to form complex life are thought to be quite different from those for carbon-based life, perhaps in worlds far, far away, with environments wildly alien to our own, where temperatures are scorching or pressures are immense. Silicon could be the fundamental building block of intricate, sentient beings. What would such life look like? How would it experience the passage of time, the warmth of a sun, or the chill of the cosmic void? Would their thoughts be crystalline structures, intricate patterns of energy flowing through mineral networks? This is not about definitive answers, but about allowing your imagination to gently sculpt new forms, new possibilities. From the raw material of scientific thought, it's a meditation on the sheer diversity that the universe might hold. A quiet acceptance that our current understanding is but a tiny window into an infinite vista. Join us, then, not on a frantic race, but on a tranquil journey through space and time. We will meander through these questions, exploring the possibilities and the profound challenges of interstellar travel. Picture yourself floating gently, untethered, observing the vast distances between stars, the faint glow of nebulae, the silent dance of galaxies. We'll touch upon the paradoxes that confound our understanding of the cosmos, Those beautiful, perplexing contradictions that invite us to rethink everything we thought we knew. These paradoxes are not obstacles, but rather gentle invitations to dive deeper, to appreciate the boundless mystery that envelops us. This quiet exploration, this gentle descent into the unknown, is designed to be an unforgettable adventure for your mind, an adventure where the destination isn't a fixed point, but a boundless sense of wonder. Are you ready to discover what lies beyond the stars? Not with a sudden jolt, but with a serene, unfolding awareness, the dream of exploring the depths of space. Venturing far beyond the familiar embrace of our own solar system has been a gentle hum in the human heart for as long as we have told stories under the moon. It's a melody of yearning, a quiet longing to stretch our understanding, to see what marvels lie just beyond the veil of our current perception. For so long, interstellar travel felt like a distant fantasy, a shimmering mirage on the horizon of our imagination, something relegated to the fantastical pages of books or the grand visions of cinema. But as you relax now, letting your thoughts drift, consider this is it truly just a distant fantasy. Or could we, in the quiet unfolding of time, genuinely achieve this monumental goal in the not-so-distant future? There's a gentle stirring in the scientific community, a subtle quickening of pace. That suggests we are indeed closer than ever to interstellar travel becoming a reality. It's not a sudden leap, but a steady, persistent progression, like the slow, deliberate turning of a grand cosmic clock. Thanks to the quiet accumulation of scientific discoveries and the relentless, often unheralded, advances in technology made in recent years, the once impossible seems to be softly, gradually, coming into view. Imagine the patient, persistent work of countless minds, toiling quietly in laboratories and observatories around the world. Their efforts, like tiny raindrops falling steadily, are slowly eroding the seemingly insurmountable barriers that once stood in our way. The development of new propulsion systems, for instance, is like discovering a more efficient way for a ship to harness the wind, allowing it to glide across vast oceans with less effort. Think of engines that don't rely on explosive forces but on subtle manipulations of fundamental particles or fields, propelling a vessel with an almost ethereal grace through the vacuum. We're not talking about noisy, fiery rockets in the traditional sense, but perhaps something far more elegant, far more in tune with the quiet mechanics of the universe itself. Then there are the advances in material science. Picture materials so incredibly light yet unbelievably strong, capable of withstanding the unimaginable stresses of interstellar speeds and the harsh realities of the cosmic environment. Imagine shields that are whisper-thin yet impervious to the tiny, high-velocity particles that pepper the void. It's like weaving a new kind of cosmic fabric, one that can cradle and protect our fragile human selves on journeys of unimaginable length. These materials are not just about strength, they're about resilience, about quietly enduring the infinite patience of space itself, and perhaps most profoundly, our ever-deepening understanding of cosmological theories brings us closer. It's as if we are slowly, gently, deciphering the ancient, silent language of the universe. The more we comprehend the fundamental laws that govern space, time, and matter, the more clearly we can envision the necessary infrastructure and technology for interstellar missions. This isn't just about building faster engines. It's about understanding the very rules of the road, the cosmic currents and eddies that will guide our way. This growing comprehension allows us to dream not just of going to the stars, but of truly understanding the path, the quiet, immense path that leads to them. However, even with these hopeful whispers and gentle advancements, this ambitious goal undeniably has its challenges. The universe, in its vast, indifferent beauty, also harbors formidable obstacles. The sheer, vast distances between stars are almost impossible to truly conceptualize. Our closest celestial neighbor, Proxima Centauri, Seems like a stone's throw away on a cosmic map, but it's a little over 4.2 light years distant. To travel at the speed of light, which is the absolute maximum speed anything can achieve in our universe, the journey would still take more than 4 years. And imagine 4 years, continuously, without stopping, without rest. Traveling at the ultimate speed limit of reality, it's a testament to the quiet immensity of space itself. And then there's the large number of threats lurking in outer space. These aren't dramatic, cinematic dangers, but rather subtle, persistent threats. Tiny, high-speed dust particles, invisible cosmic rays, unseen fields of radiation. These make interstellar travel incredibly difficult and potentially dangerous. It's like navigating a vast, beautiful, but utterly untamed wilderness, where even the smallest pebble can become a dangerous projectile at unimaginable speeds. These challenges are not meant to deter us, but to underscore the quiet reverence and immense ingenuity required to overcome them. If we allow ourselves to be optimistic, and perhaps it is not entirely unrealistic, there's a gentle possibility that humans will be able to achieve interstellar travel within our lifetime. It's a tantalizing thought, isn't it, to imagine a future where the dream of touching another star, of seeing a distant sun up close, is not just a dream but a quiet, unfolding reality for some. The possibilities that open up with such an achievement are truly endless, stretching far beyond what our current minds can fully grasp. And the rewards could be extraordinary, not just in terms of scientific discovery, but in the profound expansion of human consciousness. A quiet understanding of our place in the cosmic dance. The difficult task of interstellar travel is primarily defined by the vast expanses between stars. It's a distance that dwarfs our human sense of scale, our closest stellar neighbor. That familiar whisper in the cosmic dark is Proxima Centauri. It lies a little over 4.2 light-years away. To truly grasp what this means, let your mind drift to the concept of a light year. It's not a measure of time, but a measure of distance, the incredible distance that light, the fastest thing we know, travels in one entire Earth year. So, if we were to travel at the very maximum speed currently possible in the universe, which is the speed of light, a journey to Proxima Centauri would still take more than 4 years. 4 years of continuous, unfathomable speed, without pause, without a single moment of slowing down. It's a silent testament to the truly immense, almost oppressive distances that separate us from even our nearest stellar kin, despite all our contemporary advancements in technology, all the clever machines and brilliant minds. Achieving these speeds is still, for us, impossible. Our fastest spacecraft, our most ingenious propulsion systems, can only muster a tiny fraction of that ultimate cosmic velocity, even with what we consider to be the most advanced propulsion technology currently available, like nuclear ion propulsion. A spacecraft would still take decades, if not centuries, to reach the nearest stars. Imagine a journey that stretches not just beyond your lifetime, but beyond the lifetimes of your children, and perhaps even their children. It's a generational commitment, a quiet, almost spiritual act of faith in the future to gently overcome this monumental problem. The most hopeful option is to develop new engine technologies that can achieve much greater speeds. It's like searching for a new secret, a new whisper from the laws of physics that allows us to bend the rules of cosmic travel just a little. Various concepts on how to achieve that are being gently considered, each one a shimmering possibility in the vast expanse of scientific thought. There's the captivating idea of using antimatter, a substance so elusive and powerful that its very mention feels like a secret. Then there's thermonuclear fusion, the very process that powers the sun and other stars, a controlled miniature sun propulsion system right on our spacecraft, and in the most audacious of dreams. There's even the thought of harnessing the immense forces of black holes, those silent, gravity-devouring behemoths of the cosmos. Each of these ideas is a testament to human ingenuity, a quiet refusal to accept the boundaries that seem to be set. Let's gently consider nuclear fusion, the process that lights up our sun and the countless stars scattered across the universe. It involves the subtle combining of two light atomic nuclei, perhaps like two tiny drops of water, merging to form a slightly larger one. But in this cosmic dance, it's often hydrogen nuclei that combine to form a heavier nucleus. And in that gentle merging, a tremendous amount of energy is released on Earth. This technology is still in its infancy, a fragile seedling of an idea, but it holds the profound potential to provide an almost limitless source of energy. Imagine a source of power so abundant, so clean, that it could fuel our journeys to the stars with an almost effortless grace. It could be used to power spacecraft engines, gently pushing us through the cosmic ocean with a steady, quiet force. However, as we allow our minds to drift through these tantalizing possibilities, a quiet realization settles these feats of technology are still purely theoretical. They are beautiful concepts, intricate tapestries woven from equations and hypotheses. But there is no telling whether they will ever be possible in practice. Or, perhaps even more importantly, safe enough to use. The thought of containing a miniature sun, or manipulating antimatter, within a spacecraft is a profound one, hinting at powers both magnificent and potentially terrifying. The complexity of interstellar travel as a concept is further intensified by the astronomical amount of fuel and energy required to travel such truly great distances. Our traditional rocket propulsion technology, the kind that launched us to the moon, relies on truly huge amounts of fuel, a vast ocean of propellants. Propelling spacecraft at a speed that is only a tiny fraction of the speed of light. Think of the Parker Solar Probe, a marvel of human engineering. Currently the fastest traveling spacecraft ever built by humans. It can reach an incredible speed of 119.4 miles per second. For reference, if you were to whisper that number into the vastness of space, it's only 0.064% of the speed of light, a mere whisper compared to the roar of light itself. In order for us to gently reach Alpha Centauri within a human lifetime, or perhaps even less, we need to quietly figure out how to develop a speed of at least 10% of the speed of light. That's a monumental leap, a gentle push towards an unimaginable velocity. Yet, here lies a truly paradoxical nature of this task. It's a quiet, frustrating loop. In order for us to increase the speed of the spacecraft, to glide through the cosmos with more haste, we need more fuel. It seems logical, doesn't it? More power, more push, but by carrying more fuel on board the ship. The weight of the vessel increases, and as the weight increases, it subsequently reduces its speed. It sounds like a vicious circle, a gentle, inescapable trap that the laws of physics seem to have laid for us. More fuel means more weight, which means slower speeds, which means we need even more fuel. It's a quiet, humbling reminder of the intricate balance of the universe. Nuclear or ion propulsion engines are currently the most advanced propulsion technology available to us. A soft hum of progress in the quiet backdrop of scientific endeavor. They offer much greater efficiency in terms of fuel consumption compared to traditional rockets, like a carefully measured sip instead of a thirsty gulp. But even with their enhanced efficiency, they still require a significant amount of fuel to generate the required power. The problem isn't entirely solved, merely softened. To gently overcome these persistent obstacles, researchers are quietly developing completely new propulsion technologies that could harness the energy sources readily available in space itself. Imagine tapping into the silent, immense energies that surround us. Like a clever sailor learning to use the ocean currents instead of just relying on the wind. For instance, scientists are exploring the possibility of using solar sails. Picture a vast, shimmering sheet, lighter than air, stretched taut across the vacuum of space, using the gentle pressure of energy coming from the sun, much like a regular sail uses the wind. to ensure the continuous, silent acceleration of the spacecraft. It's a beautifully elegant concept, a gentle push from the very light that sustains us. Another solution that's been gently put forward is to use antimatter propulsion. This concept is truly captivating, a whisper of immense power contained within the very fabric of existence. Antimatter propulsion would allow the spacecraft to achieve much greater speeds while consuming far less fuel. Imagine reaching incredible velocities with just a fraction of the mass you'd otherwise need for propellants. Antimatter is a unique substance that holds a profound secret. It has the same mass as regular matter, but with the opposite electric charge. It's like a mirror image of reality, subtle yet fundamentally different when matter and antimatter come into contact. They don't just repel or mix, they annihilate each other, disappearing in a silent flash, releasing truly tremendous amounts of energy. This isn't an explosion in the fiery sense, but a complete conversion of mass into pure energy, a cosmic whisper of power. Theoretical calculations softly suggest that a spacecraft functioning on antimatter could potentially reach up to 90% of the speed of light. Imagine that. Almost the ultimate speed limit of the universe. This would mean it could reach Proxima Centauri, our closest stellar neighbor, in just over 4 years, a human lifetime. For a journey that once seemed to demand millennia, scientists have been conducting quiet experiments with antimatter for decades, gently probing its secrets. One of the earliest experiments involved creating antiprotons, which are the antimatter equivalent of protons. Those fundamental building blocks of all matter. The very first antiprotons were generated in 1955 by a group of scientists at the Lawrence Berkeley National Laboratory in California. A quiet, momentous achievement in the annals of science. However, as with many profound discoveries, antimatter is currently very costly and difficult to produce. It's like trying to gather sunlight one ray at a time. The technology to use it for propulsion is still at an experimental stage. A delicate seedling of an idea. Furthermore, antimatter is highly unstable and difficult to store. Its particles simply cannot be stored in a traditional container, as they would quickly come into contact with regular matter and annihilate each other, vanishing in a silent burst of energy instead. Ingenious magnetic fields were developed specifically for the task of capturing and storing antimatter. Imagine invisible magnetic cages, holding these elusive particles in a delicate, precisely controlled suspension, preventing them from ever touching a single atom of ordinary matter. To gently sum up this vast, complex challenge, the need for large amounts of fuel and energy for interstellar travel poses truly enormous challenges for progress. It's a fundamental barrier that whispers its presence in every calculation. However, the quiet, persistent effort to develop completely new propulsion technology or to find ways of harnessing energy from sources available directly in space is definitely a necessary push in the right direction. It's a journey into elegance, into efficiency, into understanding the universe's own subtle power. Once we find a way to travel fast enough, to glide through the cosmos with a gentle, unimaginable speed, we still won't be entirely ready for interstellar travel, because even Columbus, in his audacious search for a new route to India, did not travel blindly into the unknown. He had maps, however imperfect, and instruments to guide him. The silent, fundamental need for navigation and communication during interstellar travel presents another major, perhaps even more intricate, challenge for manned missions. Imagine being adrift in an ocean so vast, so incredibly immense, that your radio signals take years, perhaps even decades, to reach home. The great distances between stars mean that there could be significant delays in communication with Earth. This would make real-time communication incredibly difficult, if not utterly impossible. Picture trying to have a conversation where each word takes 4 years to reach its listener, and another 4 years for a response. It's a concept that stretches our understanding of connection. Furthermore, signals from Earth could be faced with interference, noise, or they could become completely lost in the vast cosmic ocean, making data acquisition and interpretation incredibly difficult. It's like trying to hear a faint whisper across a roaring storm. To gently resolve these profound issues, spacecraft will require advanced communication and navigation systems capable of handling the unique, quiet demands of interstellar travel. One possible way to achieve this subtle yet monumental feat is to use a network of interstellar satellites. Imagine a chain of quiet cosmic beacons, strung across the vast distances, that could relay information between Earth and the ship, ensuring faster and more reliable communications. It's like building a quiet, invisible highway of information across the stars. Another promising solution, almost magical in its implications, is quantum communications technology. This technology uses entangled quantum particles to transmit information instantaneously over truly long distances, bypassing the very speed limit of light itself for information transfer. This technology could revolutionize interstellar communications, allowing real-time transmission of data without any delay or interference. It's a concept that hints at a deeper, more interconnected reality. Another option, a comforting whisper of intelligence, is to use advanced artificial intelligence. This AI could help spacecraft navigate the vast expanses between stars and adjust course as needed. Even without any direct involvement of a human controller, imagine an unseen, ever-vigilant mind guiding the ship with an almost intuitive understanding of the cosmos. Accurate navigation is key for successful interstellar travel. Even the slightest deviation, a mere whisper off course, can throw a spacecraft off course for millions of miles over such immense distances. To gently minimize the risk of this happening, the ships will need incredibly accurate navigation systems, such as ones using pulsars as reference points. Pulsars, those highly magnetized, rotating neutron stars, emit beams of electromagnetic radiation from their poles. Think of them like cosmic beacons, silent, steady lighthouses in the dark ocean of space. As the pulsar rotates, it sends out a beam of radiation that shoots through space, creating a so-called momentum. Pulsars are incredibly reliable and predictable, making them ideal candidates for deep space navigation. Like the most perfect, unblinking stars on a cosmic map. For example, the technology of gravity assist trajectory, a subtle dance with celestial mechanics, was gently used on the New Horizons spacecraft mission to Pluto. It relied on Jupiter's immense gravitational forces to guide the spacecraft to its distant target, a silent, elegant slingshot across the solar system. However, as with any complex system, there is always a quiet risk of hardware malfunctioning in some way, without human intervention in real time. These failures can have catastrophic consequences, potentially leading to the loss of the crew and the mission as a whole. That is why, in the quiet absence of accurate and reliable communication and navigation systems, a mission to the nearest stars would not have any hope of success. It's a gentle reminder that even the most advanced technology requires the steady hand of foresight and preparedness. But no matter how highly equipped the ship is, no matter how much ingenious technology hums beneath its sleek exterior as it rushes towards distant stars, the most important component of the mission still remains the people on board. It is a quiet truth, a gentle reminder that at the heart of every grand human endeavor lies the fragile, resilient spirit of humanity itself. The most important, and perhaps most intricate, task in interstellar travel is to provide the crew with sufficient resources to survive during the journey. This isn't merely about packing enough supplies, it's about creating a miniature self-sustaining world, a quiet bubble of life drifting through the vast, indifferent void. This includes developing complex life support systems that could provide enough food, water, and oxygen for decades, perhaps even centuries. With current technology, we are only capable of storing a limited amount of resources, certainly not enough for truly long journeys that would span generations. Imagine trying to carry every single drop of water, every morsel of food, every breath of air needed for a voyage lasting hundreds of years. The sheer volume and weight would be utterly prohibitive. Therefore, we quietly, persistently, need new technologies and innovative ways to sustain life while traveling over a long distance. It's like a grand, quiet puzzle, where every piece is vital to the survival of those who dare to venture so far. One potential solution, a hopeful whisper in the scientific community, is to develop regenerative life support systems. Picture a closed loop, an intricate miniature ecosystem where waste is not simply discarded, but recycled and converted into useful resources. This would involve highly efficient processes for water purification, air regeneration, and even waste decomposition, turning what is no longer needed back into something life-sustaining. Additionally, the development of advanced food growing and oxygen-producing systems aboard spacecraft is an absolute must in research. Imagine compact, highly efficient hydroponic farms, bathed in soft, artificial light, quietly producing fresh food, or bioreactors gently churning out oxygen, all within the confines of a starship. It's about learning to farm the void, to coax life from the very edge of nothingness. Another intriguing option, one that often feels like a gentle dream from ancient tales, is to put astronauts into deep sleep for the duration of their journey. Similar to the way animals hibernate in winter, scientists are exploring the use of this technique, often referred to as suspended animation or hibernation. Imagine lying down, allowing your body's processes to slow to a whisper, conserving energy and resources, only to awaken decades or centuries later, refreshed and ready to continue the mission. While the idea is profoundly appealing, at the moment it presents significant medical challenges. How do we keep the crew in this suspended state for long periods of time without causing serious health issues? Without the body deteriorating in ways we don't yet fully understand, the delicate balance of human physiology, the intricate dance of cells and organs, is a complex thing to simply press pause on. However, if perfected, this method could significantly reduce the resources and life support systems required, making the impossible seem just a little more within reach. Moreover, a quiet but persistent concern is the prolonged exposure to zero gravity. Our bodies, beautifully adapted to the gentle, constant pull of Earth's gravity, are simply not designed for long periods of weightlessness. It leads to muscle atrophy, a gradual wasting away of strength, loss of bone density, making bones fragile and brittle, and numerous other physical changes that are detrimental to long-term health. Therefore, to maintain the health of the crew during the journey, physical exercise and medical intervention may be required to counteract the negative effects of zero gravity. Imagine daily rigorous routines, perhaps even specialized equipment designed to simulate resistance in a weightless environment. What may ultimately help? A comforting whisper of stability. Is an artificial gravity system in place? One elegant way to achieve that is to maintain the constant rotation of the spacecraft. Picture a large, slowly spinning ring, endlessly turning, creating a gentle outward force. The centrifugal force created by this rotation can effectively mimic the gravitational force that we experience on Earth. This approach has been researched and successfully tested on various space missions, including the quiet triumphs of Skylab and the International Space Station. Albeit on a much smaller scale, it's a way of bringing a little piece of home, a little piece of Earth's embrace. With us on our cosmic voyages, another major health concern, a silent, pervasive danger when it comes to interstellar travel, is radiation. Space, in its vast, beautiful emptiness, is also riddled with an endless array of radioactive emissions. Imagine an invisible storm, constantly buffeting anything that dares to venture beyond Earth's protective shield. Long-term exposure to these emissions poses a significant health risk to astronauts, outside of Earth's protective magnetic field, which acts like a giant, invisible shield. Humans are exposed to high levels of ionizing radiation, including powerful cosmic rays and sudden, unpredictable solar flares. Radiation, in its insidious way, causes damage to human cells, leading to various health problems, including devastating cancers and other debilitating illnesses. Additionally, prolonged exposure to cosmic radiation can cause genetic damage to DNA that can potentially be passed to future generations. A quiet, alarming legacy of cosmic travel. To gently reduce the risk associated with radiation exposure, interstellar spacecraft must be designed in a way that effectively shields the crew. This shield must be incredibly strong, capable of blocking harmful radiation, while at the same time being light enough so as not to significantly increase the overall weight of the spacecraft. A delicate balance of protection and efficiency. It must also be adapted to all types of radiation that the spacecraft may encounter during its journey. A comprehensive, silent guardian. To address these complex issues, researchers are quietly exploring various options for protection against radiation, including the imaginative use of artificial magnetic fields, which could deflect charged particles away from the ship, as well as advanced technologies and specialty materials specifically designed to absorb or neutralize harmful rays. In addition, the crew may need to take special medications or undergo medical procedures to gently reduce the effects of radiation sickness, offering a final layer of defense against the invisible dangers of the void. In addition to the tiniest radiation particles, another distinct danger you may encounter during interstellar travel are debris and asteroids. Imagine tiny, unseen bullets hurtling through the vacuum at unimaginable speeds. Asteroids and comets pose a significant threat to the spacecraft because they are often difficult to detect and even harder to avoid. Space debris, even a small item, if moving at a high speed, can cause catastrophic damage to the ship, potentially tearing through its hull with ease, to ensure the safety of astronauts and the spacecraft itself. Some form of protection is absolutely required, shielding the spacecraft from these silent, sudden dangers can be achieved through a variety of methods. This includes building thick walls capable of absorbing impacts, and using material that would absorb or deflect radiation and debris, acting like a robust, unyielding skin. Additionally, the spacecraft could be equipped with sensors and detection systems to help identify potential hazards far in advance and allow the ship to gently maneuver to avoid them. Imagine an all-seeing eye, constantly scanning the darkness for lurking dangers. However, we are once again faced with a quiet, persistent challenge. The materials needed for effective protection are rather heavy, adding to the very weight we strive to reduce. Although security technologies and detection systems have advanced significantly in recent years, further research and development is quietly required to overcome these obstacles and ensure the complete safety of astronauts and spacecraft. Either way, interstellar travel is an ambitious goal that will require significant investment in resources from governments and private entities around the world. It is a commitment that whispers of human ambition on an unprecedented scale. The cost of interstellar travel will be immense, encompassing the research and development of new propulsion systems, creating intricate life support systems, designing sophisticated navigation and communications technology, and developing robust protection from radiation and interstellar hazards, and so much more. The cost of developing the necessary infrastructure and technologies is likely to be prohibitive, requiring not just financial commitment but also a profound, shared vision. It will undoubtedly require significant cooperation and commitment from the global community. Imagine all nations, all peoples, quietly working together, pooling their resources and their ingenuity for a common grand endeavor. Grand. It's also possible that conflict of interest or opposing investor agendas could cause controversy and impede progress. Introducing a discordant note into the quiet harmony of cooperation. This could ultimately limit the scope of interstellar research and development, slowing the gentle unfurling of our cosmic dreams. One possible solution to help offset the astronomical cost of interstellar travel could be the development of space mining technology. Imagine venturing to nearby asteroids and other celestial bodies, not for conquest, but for valuable resources. Space mining involves extracting valuable resources from asteroids and other celestial bodies, which could potentially provide funding for interstellar missions. Turning cosmic dust into a silent, golden stream of investment. Furthermore, advances in space manufacturing and 3D printing could make it possible to create spacecraft and other materials directly in outer space, reducing the incredible cost and effort of launching them from Earth. It's a vision of building our future among the stars, rather than always from our home planet, without a long-term commitment to developing the necessary infrastructure. Technologies and resources. Interstellar travel may quietly remain out of reach for humankind, a beautiful dream forever just beyond our grasp. Conceptually, a completely different approach to interstellar travel, one that whispers of immense patience and a profound commitment to the future, is the construction of a generation ship. Imagine not a vessel designed to race across the cosmos in a fleeting moment, but a self-contained world, a true ark in the vast ocean of space, carrying not just a crew but entire generations of humanity. A generation ship is a hypothetical spacecraft for interstellar travel requiring an indefinite number of generations before they finally reach their ultimate destination. It's a dream of continuity, a quiet, flowing river of life stretching across unimaginable spans of time, instead of trying to reach a destination within the lifetime of the initial crew. These spaceships would carry generations of passengers who are born, live their entire lives, and eventually pass away on the spacecraft itself. Picture children born under artificial lights, never having felt the sun's natural warmth. Their understanding of a home being the intricate, enclosed world of the ship, their parents, and their parents before them, would have been born there too. Their history inextricably linked to the slow, relentless journey through the cosmic void. The generation spacecraft concept has been proposed as a potential solution to some of the most profound challenges of interstellar travel, including the vast, almost insurmountable distances and the inherent limitations of current propulsion technology. It's an acknowledgement that perhaps, for now, we cannot conquer distance with speed, but we can conquer it with time, with the gentle, persistent unfolding of generations. By allowing multiple generations of passengers to be born and raised during the journey, one can envision a scenario in which the crew can maintain the necessary resources and technology to complete the mission, even if it takes an extremely long time. Imagine the quiet, continuous transfer of knowledge, the slow evolution of culture within the confines of the ship, all dedicated to the ultimate, distant goal. It's a profound act of collective endurance, a testament to the enduring human spirit. However, this magnificent concept is not without its own quiet flaws and complex considerations. We would need to resolve fundamental issues of recruiting and managing crew across such vast spans of time. How do you select people for a journey that will stretch far beyond their own lives? How do you maintain morale, purpose, and social order over centuries? Then there's the intricate dance of allocating resources within a closed system. Every calorie of food, every drop of water, every breath of air would need to be meticulously managed and recycled, and perhaps most profoundly, the immense challenge of maintaining social cohesion over long periods of time. Imagine the quiet, slow shifting of values, the potential for new societal norms, new conflicts, to arise within a completely isolated, self-sustaining community, generations removed from the original Earth. Moreover, there's a subtle but significant possibility that the knowledge and technology needed for the mission may degrade or be lost over time, like an old manuscript slowly fading into obscurity, which could jeopardize the success of the mission as a whole, despite these deep issues. The concept of generation spacecraft remains a popular topic in science fiction and theoretical discussions about interstellar travel. A persistent whisper of what might be, a gentle reminder of the human desire to endure and explore, to sum everything up as we gently drift through these vast ideas. Let's recall the classic wait-go dilemma. This is a common predicament in decision-making, a quiet fork in the path where you must choose between waiting for a potentially more desirable outcome or taking immediate action to achieve a less desirable, but still acceptable, outcome. It's a dilemma that whispers of patience versus immediate gratification. For instance, you might experience it when you're waiting at a bus stop, but the waiting time might exceed the time required to arrive at your destination in another way. Perhaps on foot. Do you wait patiently for the bus, hoping for a comfortable ride? Or do you begin walking, knowing you'll eventually get there? Even if it's more effort, this profound scenario can be applied directly to interstellar travel, presenting us with a similar, quiet dilemma. Should we launch interstellar ships now, with the technology we currently possess, knowing they will be slow and arduous, taking centuries to reach their destinations? Or should we wait, patiently, for new technologies to emerge? Technologies that will generate much greater speed and allow new ships to reach destinations faster. Perhaps within a single human lifetime, the ethical dilemma here is a deeply personal and profound one. Would it be fair to the crew of the first ships to make a senseless sacrifice, to commit to a journey of immense hardship and duration, in case the rate of technological advancement suddenly surpassed that of the first ships? Imagine the quiet burden of knowing that your immense sacrifice might be rendered obsolete by a future breakthrough. Put yourself, for a moment, gently, into the shoes of a pioneering crew member on one of those early, slow starships. You've spent decades, perhaps even centuries, in the quiet, contained world of your vessel, drifting through the silent, cold vacuum between stars. Your hair has grayed, your body has aged. Your children and grandchildren have been born and lived their lives within the ship's walls. And then, a quiet whisper filters through newer, faster ships, propelled by unimaginable technologies, may have launched after you, long after you, and arrived at your destination long before you. This dilemma raises deep questions about the value of human life, the profound responsibility for space exploration, and the ever-present importance of progress. Waiting for new technologies could undeniably lead to faster, more efficient travel, perhaps even safer journeys. But it could also mean that the first crew would suffer, or be exposed to dangers that future generations may not even have to face. Conversely, launching ships now can be seen as profoundly unfair to the pioneering crew, as they will not benefit from the same advanced technology that future generations will enjoy. Ultimately, the final decision in this quiet, profound ethical quandary will depend on how society perceives the importance of progress and research in relation to the value of human life. It is a heavy question, one that hums with the weight of our collective future. In our quiet quest to understand the vast and mysterious universe, science has long wielded the powerful tool of logic. It's like a finely honed instrument, designed to cut through confusion and reveal underlying truths. But even when using the most rigorous methods and the most advanced technologies, paradoxes inevitably arise. These are not simply problems to be solved. They are beautiful, profound contradictions that challenge our deepest understanding of the world. They are whispers from the cosmos, inviting us to look beyond the obvious. One such paradox, a question as old as stargazing itself, is the dark sky at night, if the universe is truly vast, stretching infinitely in every direction, and filled with countless shining stars. How is it possible that the sky, even far from city lights, remains dark? It seems counterintuitive. Doesn't it, like standing in an endless forest filled with fireflies, yet seeing only darkness? Then there's the nature of dark matter, an elusive substance that forever escapes the grasp of even our most advanced instruments. It exerts a gravitational pull, influencing the very structure of galaxies. Yet it remains unseen, unheard, an invisible presence shaping the cosmos. What could it be a quiet, fundamental ingredient we cannot yet perceive? And what about the inevitability of oblivion, the grand, luminous solar system we call home, along with our beautiful, living planet and ourselves, may eventually disappear into oblivion, forever lost in the vastness of time and space? It's a sobering thought, a quiet reminder of impermanence, even on a cosmic scale. These paradoxes are not just philosophical ruminations, not just abstract ideas for quiet contemplation. They have real implications for our understanding of the universe. They force us to gently reconsider our most basic assumptions and to question the things we thought we were sure of. They encourage us to go beyond our current understanding, to stretch our minds into the unknown, and to delve deeper into the quiet mysteries of the cosmos. And in the end, faced with these paradoxes, we can gain new understanding, a quiet glimmer of insight, and move forward in our comprehension of the universe. One gentle whisper at a time. Let's turn our attention to the horizon problem, also known as the horizon paradox. This is a paradox that quietly arises from the observations that the temperature of the cosmic microwave background radiation, or CMB, is practically uniform throughout space. Imagine looking out into every direction, seeing a perfectly even, gentle glow, as if the universe were bathed in a perfectly balanced warmth. This is true despite the fact that regions of the universe separated by vast distances have not had enough time to physically interact and reach thermal equilibrium. It's like finding two separate cups of tea, miles apart, that somehow cooled down to exactly the same temperature, at exactly the same time, without ever being connected. The root cause of the horizon problem is a quiet truth. The CMB is a remnant of the time the universe was in a hot and dense state, known as the Big Bang. The CMB itself is an almost perfect black body radiation, characterized by the uniform temperature of approximately 2.7 Kelvin in all directions. It's a faint, ancient whisper from the very dawn of creation. However, if the universe continued to expand for about 13.8 billion years, certain regions of the universe, separated by such vast distances, would simply not have had enough time to reach thermal equilibrium, and therefore be of the same temperature. The paradox gently suggests that the temperature of the CMB does not have to be the same throughout the universe. Yet it is. The horizon problem has quietly baffled cosmologists for decades and prompted a number of proposed solutions, each one a thoughtful attempt to reconcile the seemingly contradictory observations. One prominent solution is the theory of cosmic inflation. This theory states that the universe underwent a rapid, almost instantaneous expansion in the very early stages of its formation, like a balloon suddenly inflating at an incredible speed. This expansion would have smoothed out any initial fluctuations in temperature, gently evening out the cosmic warmth, making the temperature of the CMB about the same throughout the universe. Inflation models also gently explain the homogeneity and isotropy of the universe, two more major observational mysteries in cosmology that speak to the remarkable uniformity of our cosmos. Another possible answer, a subtle thread of thought, is the concept of causality. Causality is a fundamental principle in the sciences. It's the quiet idea that every occurrence, every action, every event is preceded by a cause that determines its effect. It's the intricate chain of events that links everything in existence. The idea here is that the early universe was in equilibrium and was much denser and hotter. In this extremely dense and hot state of the universe, photons of relic radiation were in casual contact, meaning they could interact with each other and achieve thermal equilibrium. It's like a vast, crowded room where everyone can easily talk to everyone else, allowing the temperature to even out. The third solution, a more expansive thought, is the concept of cosmic variance The gist of this idea is that the universe is much larger than we can observe, stretching far beyond our current line of sight, and that the temperature fluctuations we do see are simply statistical deviations from the average temperature of the universe in general. It suggests that if we could see more, the overall picture would look different. The horizon paradox, in its essence, is a complex and multidimensional problem that has not yet been fully resolved. Each of the proposed solutions has its own quiet strengths and gentle weaknesses, and a true resolution of the paradox may require a beautiful combination of these ideas, or even an entirely new theory, a whisper from a future understanding. Now, let's gently explore Olbers's paradox, sometimes known as the redshift paradox. This is a mystery that has quietly puzzled astronomers for centuries, a question that lingers like a faint echo from the earliest days of looking up at the night sky. Named after the pioneering German astronomer Heinrich Olbers, this paradox softly arises from the profound contradiction between the presumably infinite number of stars in the universe and the undeniable darkness of the night sky. It's like being in an endless, luminous garden, yet somehow finding yourself shrouded in shadow. The quiet gist of this paradox lies in a seemingly simple logical deduction. If the universe were truly infinite and eternal, and if stars were evenly distributed throughout the endless bounds of outer space, then in any direction we looked, our gaze would eventually land upon a star. The light from these stars, however distant, would eventually, inevitably, reach our planet. If this were the case, then the night sky should be illuminated with the same intensity as the surface of the sun, bathed in an unending, brilliant glow. Yet, despite this seemingly logical reasoning, the night sky remains dark, presenting a perplexing enigma for scientists and stargazers alike. It's a quiet challenge to our intuition, a gentle nudge to look deeper. Several possible solutions have been gently put forward to explain this profound mystery, each one a thoughtful attempt to reconcile the observed darkness with the theoretical brilliance. One solution suggests that the universe is not uniform and isotropic, meaning that the stars are not evenly distributed throughout space. Imagine patches of immense emptiness, vast cosmic deserts, where light is scarce. This could be due to the presence of large-scale structures, such as immense galaxy clusters and voids. That would create dark patches in the night sky, like giant shadows cast across the cosmic canvas. In addition, the light from the more distant stars could be absorbed by intergalactic dust, a fine, almost imperceptible veil of particles scattered across the vastness. This cosmic dust would act like a gentle filter, making the night sky appear darker. This theory is softly supported by observations of major redshifts and distant quasars, hinting at a universe that is both grand and subtly obscured. Another possible solution lies in the expansion of the universe. Picture the very fabric of space stretching, subtly, continuously, between all things. The farther back we look into the cosmos, the farther away the light sources would have been from us. When we look back into the past, the universe becomes denser, much hotter, and brighter as a result. The light from distant stars is shifted to the red end of the spectrum, a phenomenon known as a redshift, caused by the stretching of light waves as the space they travel through expands. As light is stretched, it becomes too faint to be seen by our eyes, effectively disappearing into the infrared or radio spectrum, becoming a silent, invisible hum. We can't say for sure whether our universe is infinite. It remains a profound question, a quiet whisper on the edge of our understanding. But according to the Big Bang Theory, we know one thing for sure: our universe had a beginning. It wasn't always here. It sprang into existence from a state of unimaginable density and heat. Additionally, the assumption that the universe is finite would mean that the light from distant stars does not reach us simply because our universe is constantly expanding. Because of this expansion, the wavelength of the light from distant stars is greatly stretched, and it eventually reaches Earth in the infrared range. beyond the reach of our human eyes. It would also quietly mean that the light from distant stars has either not yet managed to reach us, still on its unimaginably long journey, or that the stars themselves have already died out, their light extinguished long before it could ever touch our planet. On the other hand, if we assume that our universe is infinite, then it's quite natural that at some point, due to the constant expansion of the universe, stars and matter would begin to acquire a speed that exceeds the speed of light relative to our perspective. This would make it impossible for their light to ever reach Earth, as the space between us expands faster than light can traverse it. The enigma of the Olbers paradox remains one of the most intriguing mysteries in cosmology, a quiet challenge that invites us to think deeply. Its solution requires a deeper understanding of the very nature and structure of our universe, a continuous, gentle exploration into the heart of existence. Let's now gently turn our attention to the flatness problem. This is a paradox that quietly arises from the profound observation that the universe is almost perfectly flat. Imagine the universe as an immense, perfectly smooth sheet, without any discernible curves or ripples. This observation holds true despite the fact that the density of its matter is far from sufficient to maintain such a state. Which softly begs the question, why is the universe flat? And what exactly do we mean when we classify it as such? The flatness of the universe implies that spacetime itself is not curved, at least not on the largest scales we can observe. In a flat universe, parallel lines would remain parallel forever, and the angles of a triangle would always add up to 180 degrees. Just as they do on a flat piece of paper, it also implies that the amount of matter and energy is just right for the universe to be flat. A delicate, precise balance. However, the density of observable matter and gravitational energy in the universe are much lower than necessary to achieve this perfect flatness. If the universe's density were slightly off, it should have either expanded too quickly, becoming incredibly sparse, or collapsed back in on itself, becoming a dense, fiery point. And this, of course, makes us quietly wonder, how does the universe maintain its flat shape against all apparent odds in a nutshell? That's the essential principle of the flatness problem, a mystery that continues to haunt some of the greatest minds in the field, a persistent whisper of cosmic fine-tuning. There are several possible solutions to the flatness paradox, each one a thoughtful pathway into understanding. One potential solution is the elusive concept of dark energy. It is believed that this mysterious form of energy contributes to the acceleration of the expansion of the universe. Imagine an invisible, pervasive force gently pushing everything apart, ever so slightly increasing the distance between galaxies. Dark energy is believed to contribute a staggering 68% of the total energy in the present-day observable universe. It possesses a peculiar quality. It has negative pressure and acts as a repulsive force, subtly counteracting the gravitational force of matter and causing the universe to expand at an accelerated rate. This gentle, persistent acceleration would help to flatten the universe. Like stretching a wrinkled fabric until it becomes smooth. Another powerful solution, a whisper of a cosmic event of unimaginable scale, is the concept of inflation. According to the theory of inflation, the universe underwent a rapid, almost instantaneous expansion in the early stages of its formation, like a tiny balloon suddenly swelling to an enormous size in the blink of an eye. As space expands, the geometry of space becomes flatter. To help you understand, imagine a balloon as it fills with air and inflates. Its surface becomes smoother and flatter, even though it's still a curved surface. Similarly, if the universe inflated dramatically, any initial curvature would be stretched out, making it appear virtually flat on the vast scales we observe. This type of expansion would smooth out any initial density changes, gently evening out the cosmic landscape and making the universe nearly flat. The third solution, a more expansive and perhaps humbling thought, is the multiverse theory. which quietly suggests that our universe is just one of many. According to this theory, there are a large, perhaps infinite, number of universes, each with its own set of physical laws and initial conditions. And based on this, the likelihood that one of them will happen to be flat is much higher than if there was only one universe. It's like rolling an infinite number of dice, and one of them just happens to land perfectly. It's a concept that invites our minds to stretch beyond the single reality we perceive, into a boundless sea of possibilities. Now, let's gently consider the monopole paradox. This is yet another example of an unyielding mystery of the universe, a subtle, perplexing absence in the grand cosmic tapestry. This paradox quietly arises from the observation that there are no observable magnetic monopoles. Despite the fact that their existence is predicted by several theories of particle physics and, if they existed, they should be present in the universe. Magnetic monopoles are hypothetical particles with a single magnetic pole, either a north pole or a south pole, but never both. All known magnets in our everyday experience, from the tiny ones on your refrigerator to the Earth's own immense magnetic field, have both a north and south pole, always inextricably linked. The existence of these hypothetical particles has been predicted in grand, sweeping theories such as the Grand Unified Theory, or GUT, which seeks to unify fundamental forces, and quantum gravity theories, which attempt to merge the quantum world with the realm of gravity. However, despite great efforts and extensive research, with scientists diligently searching in accelerators and cosmic ray detectors, no magnetic monopoles have been found. Their absence is a quiet whisper, a persistent question mark in the equations of physics. Nonetheless, despite their elusive nature, there are many theories gently attempting to explain their apparent absence. One possible explanation for the absence of magnetic monopoles is their instability, a subtle fragility that causes them to decay into other particles shortly after formation, making them undetectable in the modern universe. They might have existed, fleetingly, but vanished before we could ever hope to glimpse them. Another theory quietly claims that magnetic monopoles were created during a supersymmetry transition in the early universe, but they're now too rare for us to be able to observe them. The idea is that in the incredibly hot and dense early universe, the symmetry of the laws of physics was different than it is now, perhaps more elegant, more unified. These symmetries were broken during a phase transition, similar to how water changes from a liquid to a solid when it freezes, changing its fundamental state. During this phase transition, magnetic monopoles should have appeared as a result of this symmetry breaking. However, as the universe has expanded and cooled, these monopoles have become incredibly diluted, spread out across such vast distances that they are now simply too rare to be observed. Like individual grains of sand scattered across an infinite desert, the quiet search for these hypothetical particles continues, as does the scientific work with the gentle goal to unravel the monopole paradox and deepen our understanding of the universe, one thoughtful inquiry at a time. Let's now gently ponder the entropy paradox. This is a paradox that quietly arises from the profound observation that the universe is remarkably ordered and structured. Despite the fact that the second law of thermodynamics clearly states that entropy, or in other words, disorder, must increase over time. It's a beautiful contradiction. Isn't it like watching a chaotic room spontaneously organize itself? But what exactly does entropy actually mean? We usually talk about it as if it were a measure of disorder, a quantitative representation of the randomness and chaos that exists within a system. Imagine a broken egg on the floor. It has more entropy, more disorder, than an intact egg sitting neatly on the countertop. Or picture a spoonful of cold cream gently placed into a cup of hot coffee. Initially, they have less entropy because they are distinct and separated. But once you stir them together, they mix and become uniform, and the combination has more entropy. Think of a chaotic pile of clothing strewn across a chair. It has a higher entropy than a neat set of drawers where all the clothes are folded and organized according to type and color. Entropy, in its essence, is the universe's quiet tendency towards disarray, its gentle drift towards uniformity, according to the second law of thermodynamics, a fundamental principle that underpins much of our physical world. The total entropy of an isolated system will always increase over time. This law implies that the universe, being a vast, isolated system, should become less ordered, more chaotic. As time goes by, it should steadily move towards a state of maximum disorder, where everything is uniformly distributed and no useful energy can be extracted. However, the very structure of the universe conspicuously contradicts this idea. We observe that the universe is highly ordered and structured. It contains magnificent galaxies, swirling islands of billions of stars, countless individual stars burning brightly, intricate planets orbiting them, and even complex life forms like ourselves, capable of conscious thought and creation. How can such order arise and persist in a universe that is supposedly destined for ever-increasing disorder? This is the quiet heart of the entropy paradox. There are several thoughtful theories that offer possible solutions to this paradox, each providing a different perspective on how the order and structure observed in our universe can be gently reconciled with the second law of thermodynamics. One profound solution is the concept of entropy as an arrow of time. The arrow of time is the idea that time has a distinct direction, always moving from the past and into the future, never reversing. This concept gently suggests that while entropy would indeed increase in a closed system, it doesn't necessarily happen in an open system like the universe. At the same time, the universe can still freely exchange matter and energy with the environment, which makes the second law of thermodynamics, strictly speaking, inapplicable to the universe as a whole in the same way it applies to a perfectly sealed laboratory experiment. The universe is always interacting, always breathing, always in a state of subtle exchange, perhaps allowing pockets of order to form. Another beautiful solution, known as the emergence theory, suggests that at the macroscopic level, large-scale structures and order can spontaneously emerge. Even though entropy is increasing at the microscopic level, imagine a kaleidoscope. The individual pieces are chaotic, but when you look at the larger pattern, a beautiful, ordered design emerges. This idea suggests that while entropy increases on a small, local scale, it can lead to surprising, intricate order on a larger scale. It's like a quiet dance between chaos and creation, where the seemingly random movements of individual particles can give rise to the grand, organized structures we observe. Finally, some scientists gently believe that the answer to the entropy paradox may be provided by the expansion of the universe. The continuous expansion of the universe increases the total volume of the observable universe, subtly spreading out its contents. This spreading out, in turn, can effectively reduce the entropy of the system. This means that even though entropy increases locally, within specific regions or systems, the overall entropy of the universe can remain constant or even decrease due to the universe constantly expanding. It's like drawing a picture on a balloon and then inflating it. The picture stretches and seems less dense. Even though nothing was erased, the last two theories, the expansion theory and the emergence theory, are similar in concept and could potentially complement each other in solving the entropy paradox, offering a more complete whisper of understanding. The expansion theory offers a solution to the paradox by decreasing the total entropy of the system through volume increase, while the emergence theory offers a solution by explaining how structures and order can spontaneously emerge despite an increase in local entropy. It's a beautiful intertwining of ideas, where the grand sweep of cosmic expansion allows for the delicate formation of order within its vastness. Let's now turn our gentle gaze to the information paradox. Sometimes called the black hole information paradox or Hawking's paradox. This is a profound problem in theoretical physics, one that whispers of fundamental truths in the very fabric of reality. It suggests that black holes absorb information, thereby irretrievably destroying it. But what exactly do we mean by information in the context of this paradox? It doesn't refer to secrets or data files in the human sense. Instead, it refers to quantum parameters that describe the state of a physical system. Imagine every tiny detail, every subtle vibration, every unique characteristic of a particle or a collection of particles, encoded in its quantum state. These parameters contain all the information needed to fully define the state of the system. Every nuance of its existence, they play a central, almost sacred, role in the principles of quantum mechanics, the theory that governs the strange and wonderful world of the very small. Quantum mechanics, in its elegant and precise way, believes that the entirety of information in the universe is conserved. This means that information can neither be created nor destroyed. It can be transformed, it can be hidden, it can be spread out, but it can never truly vanish. It's a fundamental principle, like the conservation of energy or mass, a quiet assurance that nothing is ever truly lost. Now, let's gently return to how this paradox arises. Black holes, those mysterious, incredibly dense regions of spacetime, are formed from the collapse of massive stars. Their gravitational pull is so immense that nothing, not even light, can escape once it crosses a boundary called the event horizon. When matter falls into a black hole, it seems to simply disappear from our universe, taking with it all its information, according to classical physics. Once something falls into a black hole, it's gone forever, and the black hole itself is characterized only by its mass, charge, and angular momentum, losing all the unique information about what fell in. This contradicts the fundamental principle of information conservation from quantum mechanics. If information is truly conserved, then what happens to the information of the matter that falls into a black hole? Does it truly vanish? Or is it somehow preserved? Perhaps in a form we don't yet understand. This is the quiet, persistent whisper of the information paradox, a deep challenge to our understanding of both gravity and quantum mechanics, two pillars of modern physics that seem to clash at the edge of a black hole. The information paradox deepens when we consider Stephen Hawking's groundbreaking work on black holes. For a long time, the prevailing wisdom, a quiet consensus among physicists, was that nothing, absolutely nothing, could escape a black hole once it had crossed the event horizon. It was a one-way cosmic street. However, Stephen Hawking, with his profound insights, proposed in 1974 that black holes are not entirely black. Instead, they emit a faint glow of particles and radiation, a phenomenon now famously known as Hawking radiation. Imagine a black hole slowly, imperceptibly, evaporating over vast stretches of cosmic time, like a dewdrop disappearing in the morning sun. Hawking's calculations suggested that this radiation carries no information about the matter that fell into the black hole. It's like a cosmic shredder, reducing everything to its most basic, featureless components. If black holes eventually evaporate completely through Hawking radiation, and this radiation carries no information, then the information about everything that ever fell into them would be irretrievably lost. This directly contradicts the fundamental principle of quantum mechanics that information must be conserved. It's a profound conflict between two of the most successful theories in physics: general relativity, which describes gravity and black holes, and quantum mechanics, which describes the behavior of matter at the smallest scales. This contradiction, this gentle clash of giants, created the information paradox. It quietly asks, where does the information go? Does it truly vanish? Violating a bedrock principle of quantum physics, or is it somehow encoded in the Hawking radiation? Perhaps in a form so subtle and complex that we cannot yet decipher it for decades. This paradox has been a major point of contention and debate among physicists, a persistent whisper of incompleteness in our understanding of the universe. There are several proposed solutions to the information paradox. each offering a fascinating glimpse into how our understanding of the cosmos might evolve. One intriguing idea is that information is not truly lost, but is encoded in a subtle way within the Hawking radiation. Imagine a message written in an incredibly complex, almost invisible code. This would mean that the radiation emitted by a black hole, though seemingly random, actually contains the complete information about everything that fell inside, just scrambled beyond immediate recognition. This concept aligns with the holographic principle, which gently suggests that all the information in a region of space can be encoded on its boundary, in the case of a black hole. This boundary would be the event horizon, a cosmic screen on which all the details of its interior are subtly projected. Another theoretical solution involves the idea of remnants. This suggests that black holes do not fully evaporate but leave behind tiny, stable remnants that contain the lost information. Imagine a tiny, incredibly dense particle, too small to observe, but carrying the entire memory of the black hole's past. These remnants would be exotic, incredibly dense objects, defying our current understanding of particle physics. However, this solution also raises new questions. How can such tiny objects store so much information? And what keeps them from continuing to evaporate? It's a gentle exchange of one mystery for another. A third, more radical solution, sometimes whispered in the furthest reaches of theoretical physics, is that the information is transferred to a parallel universe. Imagine a subtle tear in the fabric of space-time, allowing information to leak into another reality. This idea, deeply embedded in the concept of a multiverse, suggests that when matter falls into a black hole, its information isn't destroyed but simply exits our universe, perhaps appearing in another. This concept is highly speculative, inviting us to stretch our imaginations far beyond the familiar. Each of these proposed solutions offers a different pathway to resolving the paradox, but none have been definitively proven. The information paradox remains a quiet, profound challenge, pushing us to refine our understanding of quantum gravity and the fundamental nature of reality itself. It's a puzzle that continues to inspire deep thought and quiet contemplation. Now, let's allow our minds to drift gently to a concept that challenges our very perception of emptiness, the vacuum energy paradox. Also known as the cosmological constant problem. Imagine, for a moment, the quietest, emptiest space you can possibly conceive. A place devoid of matter, devoid of light, utterly nothing, according to classical physics. Such a vacuum would indeed be truly empty. However, quantum field theory, a cornerstone of modern physics, paints a very different picture. It suggests that what we perceive as empty space is, in fact, teeming with activity. Quantum field theory, in its subtle way, predicts that empty space, or the vacuum, is not truly empty but is filled with virtual particles constantly popping into and out of existence. Imagine a silent, cosmic foam, bubbling with ephemeral particles that appear for a fleeting moment and then vanish back into the void. These quantum fluctuations give rise to what is called vacuum energy, an inherent energy density of empty space itself. It's like a quiet, pervasive hum woven into the very fabric of reality. The paradox arises when we try to quantify this vacuum energy. Theoretical calculations based on quantum field theory predict an enormous amount of vacuum energy, an incredibly vast density that is so immense, it's almost incomprehensible. This theoretical prediction is greater than what cosmologists actually observe by a factor of 10 to the 120s. To put that into perspective, that's a 1 followed by 120 zeros. An astronomical discrepancy, a quiet shout in the face of our understanding. If this predicted vacuum energy were real and its effects were as strong as the theories suggest, it would cause the universe to expand at an incredibly accelerated rate, so fast that galaxies and stars would never have formed. And the universe would be a cold, empty, rapidly diluting void. Clearly our universe, filled with its beautiful, intricate structures, is not expanding in that frantic way. This enormous discrepancy between the theoretical prediction and the observed value of vacuum energy is the vacuum energy paradox. It's a profound challenge to our understanding of the universe, suggesting a deep inconsistency in our current physical theories. Why is the vacuum energy we observe so incredibly small, almost negligible? Compared to what our theories predict, it's a quiet whisper of a missing piece in our cosmic puzzle. Several solutions have been gently proposed to address this paradox. One idea suggests that there might be an underlying symmetry in nature that cancels out most of the vacuum energy. Imagine a delicate balance of forces, perfectly designed to neutralize the overwhelming theoretical energy, leaving behind only the tiny amount we observe. This would imply that there's a deeper, more elegant structure to the laws of physics that we haven't yet discovered. This is often linked to theories like supersymmetry, which posits that every known particle has a heavier, unseen partner, and their quantum fluctuations might cancel each other out in a beautiful cosmic ballet. Another fascinating solution, deeply embedded in the concept of the multiverse, is the anthropic principle. This principle suggests that our universe's vacuum energy is so small because, if it were much larger, life as we know it would not exist. Imagine an infinite number of universes, each with a different value of vacuum energy. Only those universes with an incredibly tiny, finely tuned vacuum energy would allow for the formation of stars, galaxies, and planets, and thus, for the emergence of life. Therefore, we find ourselves in one of these Goldilocks universes simply because we wouldn't be here to observe it otherwise. It's a quiet, humbling thought our very existence might be the reason for the universe's delicate balance. A third avenue of exploration involves modifying our understanding of gravity itself. Perhaps Einstein's theory of general relativity, while incredibly successful, needs a subtle adjustment on cosmic scales. Some theories propose that gravity behaves differently at very large distances, which could explain why the universe expands at a moderate rate despite the predicted vast vacuum energy. This would require a profound rethinking of space-time, a gentle reimagining of the cosmic stage. The vacuum energy paradox remains one of the most significant unsolved problems in theoretical physics. A quiet challenge that invites us to delve deeper into the fundamental nature of reality, constantly pushing the boundaries of our knowledge. Let's now allow our thoughts to gently drift to the Fermi paradox. This paradox, named after the physicist Enrico Fermi, poses a quiet, profound question about the apparent contradiction between the high probability of the existence of extraterrestrial civilizations and the lack of observational evidence for them. Imagine the sheer, vast number of stars in our galaxy alone, hundreds of billions, and then consider that many of these stars likely host planets, given the immense age of the universe, and the likelihood that life might have arisen on many of these planets. It seems statistically probable that at least some of these life forms would have evolved into advanced, intelligent civilizations, perhaps far older and more capable than our own. If so, where are they? Why haven't we detected any signs of their existence? No radio signals, no megastructures, no evidence of their presence anywhere in the cosmos. This is the quiet, nagging question at the heart of the Fermi paradox. The logic is simple yet compelling. If intelligent life is common, then the universe should be teeming with it. Civilizations much older than ours would have had ample time to develop interstellar travel, to colonize their galaxies, or at least to emit detectable signs of their existence. Yet, as we listen intently to the cosmic silence, we hear nothing. This silence is the core of the paradox. Many possible solutions, each a thoughtful whisper in the quiet debate, have been proposed to resolve the Fermi paradox. One category of solutions suggests that intelligent life is simply much rarer than we think. This is known as the rare Earth hypothesis. Perhaps the conditions necessary for complex life to evolve, from the precise planetary formation to the long-term stability of a climate suitable for life, are so incredibly specific and rare that Earth is, indeed, a truly unique exception. It's a humbling thought, making our existence feel even more precious and improbable. Another set of solutions revolves around the concept of a great filter. This idea posits that there is some immense, perhaps insurmountable, barrier that prevents life from reaching a very advanced stage. This filter could be in our past, making the emergence of complex, intelligent life incredibly difficult, perhaps the leap from single-celled to multicellular life, or the development of sentience itself, is far more improbable than we imagine, or more sobering. The great filter could lie in our future. It could be a cataclysmic event, like a self-destruction through advanced technology, or an unavoidable cosmic disaster. That prevents intelligent civilizations from surviving long enough to become interstellar. This is a quiet, cautionary tale for humanity itself. A third category of solutions suggests that extraterrestrial civilizations might exist, but we simply haven't detected them yet, or they are deliberately hiding from us. Perhaps they are so advanced that their communication methods are beyond our current comprehension, like trying to pick up a subtle cosmic thought wave with an ancient radio. Or maybe they are practicing a zoo hypothesis, observing us from afar without interfering, treating Earth like a protected cosmic wildlife preserve. Another possibility is that the universe is simply too vast, and even advanced civilizations are too far apart for their signals to reach us, or for us to find them. It's like searching for a single whisper in an infinite, silent cathedral. The Fermi paradox continues to be a profound source of contemplation, inviting us to ponder our place in the cosmos and the myriad possibilities that the universe may hold, known and unknown. Let's now allow our minds to gently drift to the grandfather paradox. This is a classic paradox, deeply embedded in the very fabric of our understanding of time and causality, especially when we consider the mind-bending possibility of time travel. Imagine, for a moment, a quiet journey back through the swirling mists of time. Not just to a distant historical event, but to a moment that directly affects your own existence. The paradox states that if a person were to travel back in time and prevent their own grandfather from meeting their grandmother, then that person would never be born. But if they were never born, how could they have traveled back in time to prevent the meeting in the first place? It's a self-contradictory loop, a silent, dizzying dance of logic that seems to break the very rules of cause and effect. The core of the paradox lies in the concept of causality, the fundamental principle that every event has a cause that precedes it, and this cause determines its effect. If you alter a past event that is a necessary cause for your present existence, you create a logical impossibility. It's like trying to cut the branch you're sitting on. If you succeed, you fall. But then you couldn't have cut the branch in the first place. This paradox suggests that time travel, at least in its simplest, most direct form, might be impossible. Or that if it were possible, it would operate under very strict, perhaps unimaginable, rules that prevent such causal loops. It's a quiet whisper of the universe saying, some things are simply not meant to be changed. Many thoughtful solutions have been gently proposed to resolve the grandfather paradox, each one a fascinating exploration of the nature of time itself. One of the most popular and perhaps intuitively satisfying solutions is the multiverse theory, also known as the many worlds interpretation of quantum mechanics. This theory suggests that every time a decision is made, or every time a quantum event occurs, the universe splits into multiple parallel universes, each representing a different possible outcome. In the context of time travel, if you were to go back in time and prevent your grandfather from meeting your grandmother, you wouldn't be erasing your own existence in your original timeline. Instead, you would simply be creating a new, alternate timeline or parallel universe where that event happened differently. In this new branch of reality, you might indeed never be born, but your original self, from the original universe where you were born, would continue to exist, unaffected. It's like stepping onto a different path, where your actions create a new reality, leaving your old one undisturbed. This solution elegantly avoids the logical contradiction by simply asserting that there isn't one timeline to break, but an infinite number of possibilities. Another proposed solution is the Novikov self-consistency principle. This principle, a more subtle and perhaps deterministic view, suggests that if time travel were possible, any actions taken by a time traveler would automatically be consistent with past events, preventing any paradoxes from occurring. It means that if you were to travel back in time with the intention of changing something, the universe itself, through its intricate laws, would subtly conspire to prevent you from doing so, or would ensure that your actions somehow lead to the very outcome that already happened. For example, if you tried to prevent your grandfather from meeting your grandmother, perhaps you'd accidentally introduce them, or your attempt would somehow lead to their eventual meeting. It's like an unseen hand gently guiding events, ensuring that causality remains unbroken. This principle implies that free will in the context of time travel might be an illusion, or that the universe possesses an inherent self-correcting mechanism. A third, more abstract solution lies in the nature of space-time itself, suggesting that perhaps space-time is not just a stage for events, but a fixed, unchanging entity, a block universe where all moments past, present, and future exist simultaneously. In this view, time travel wouldn't involve changing the past, but simply experiencing different parts of this unchanging block. If the past is already there as a fixed part of this block, then you can't truly alter it, only visit it. Your actions in the past would already be a part of that fixed past, implying a predetermined reality. This concept makes the grandfather paradox simply impossible, as the very act of changing the past is a misunderstanding of how time works in this framework. The grandfather paradox, in all its perplexing beauty, remains a powerful thought experiment, urging us to consider the profound implications of time travel and the intricate, often mysterious, nature of time itself. It's a quiet reminder of how much we still have to learn about the most fundamental aspects of our existence. Let's gently consider the cosmic censorship hypothesis. This is a truly fascinating concept in general relativity, a subtle whisper about the hidden parts of our universe. It's a hypothesis, not a proven fact. That was first proposed by the brilliant physicist Roger Penrose. Imagine, for a moment, that gravity can become so incredibly strong, so overwhelmingly powerful, that it creates what are called singularities, points in space-time where density and curvature become infinite, where the laws of physics as we know them break down. These singularities are often found at the heart of black holes. The cosmic censorship hypothesis, in its gentle yet profound way, states that these singularities are always hidden from our view, always cloaked by an event horizon. An event horizon is that boundary around a black hole beyond which nothing, not even light, can escape. It acts like a cosmic veil, shielding the naked singularity from the rest of the universe. So, in essence, the hypothesis suggests that there are no naked singularities, no singularities that are directly observable from the outside. Without being enclosed by an event horizon, why is this important? Because if naked singularities existed, they would present a severe problem for the predictability of physics. If you could observe a naked singularity, you could theoretically witness events where the laws of physics simply cease to apply. Where cause and effect break down, this would allow for unpredictable and potentially chaotic outcomes, destroying the very determinism that underpins much of our scientific understanding. It's a quiet fear among physicists, the idea that the universe might contain regions where its own rules unravel without warning. The hypothesis essentially acts as a cosmic censor, preventing such bad behavior from affecting the observable universe It's a gentle assumption that the universe is orderly and fundamentally predictable. However, the cosmic censorship hypothesis is still an unproven conjecture, despite extensive research and countless thought experiments. Physicists have not been able to definitively prove it, nor have they managed to find a definitive counterexample. It remains one of the most significant unsolved problems in general relativity, a persistent whisper of mystery. There are several thoughtful reasons why the cosmic censorship hypothesis might hold true. One idea is that the formation of an event horizon is an inevitable outcome of gravitational collapse. Imagine a star collapsing under its own immense weight. The hypothesis suggests that before the singularity ever becomes naked, an event horizon would always form around it, subtly wrapping it in an invisible cloak. This implies that the very dynamics of gravity naturally lead to the concealment of singularities. Another argument for the hypothesis is that its violation would lead to fundamental problems for causality and predictability in the universe. If we could see a naked singularity, events could emerge from it seemingly without cause, or information could simply disappear into it, violating the cherished laws of physics. The hypothesis, therefore, helps to preserve the integrity of our physical theories and maintains a universe where scientific predictions are possible. It's a comforting thought, a gentle reassurance that the cosmos follows discernible rules. Conversely, there are also quiet arguments and theoretical models that gently challenge the cosmic censorship hypothesis. Some mathematical solutions to Einstein's field equations, which describe gravity, do seem to allow for the possibility of naked singularities under certain extreme conditions. These are often highly idealized scenarios, perhaps not perfectly reflecting the complex reality of our universe, but they indicate that the concept of a naked singularity is not entirely forbidden by the mathematics. This suggests that the universe might be more complex, more surprising than we currently assume. The existence, or non-existence, of naked singularities has profound implications for our understanding of gravity, black holes, and the very structure of space-time. If naked singularities exist, it could mean that our current understanding of general relativity is incomplete, or that we need a new theory of gravity to describe what happens at these extreme points. It's a quiet invitation to rethink the very foundations of our cosmic knowledge. The cosmic censorship hypothesis, therefore, remains a vital area of research, a continuous, gentle exploration into the deepest, most enigmatic corners of the gravitational universe. It's a testament to the fact that even in the most well-established theories, there are still profound mysteries waiting to be unraveled. Now, let's gently turn our thoughts to the measurement problem in quantum mechanics. This is one of the most perplexing and mind-bending paradoxes in all of physics. A quiet, almost unsettling whisper about the nature of reality itself. Imagine the world of the very small, the realm of particles and waves, where things behave in ways that defy our everyday intuition. According to quantum mechanics, a cornerstone of modern physics, particles do not exist in a definite state until they are measured. Instead, they exist in a superposition of all possible states simultaneously. It's like a particle being in all possible places at once, or spinning both clockwise and counterclockwise at the same time. This state of superposition is described by a mathematical entity called a wave function. The paradox arises when we ask, what actually constitutes a measurement? And how does this act of measurement cause the wave function to collapse into a single, definite state, abandoning all other possibilities? Imagine a particle existing as a fuzzy cloud of possibilities. And then, the moment you look at it, it suddenly snaps into being a single, definite point. This mysterious process, known as wave function collapse, is not clearly defined or explained by quantum mechanics itself. It's the elephant in the room of quantum theory, a silent, profound question that has no easy answer. Consider Schrödinger's famous cat, a thought experiment often used to illustrate this paradox. Imagine a cat placed in a sealed box with a radioactive atom. a Geiger counter, a hammer, and a vial of poison if the atom decays. The Geiger counter detects it, the hammer breaks the vial, and the cat dies. If the atom doesn't decay, the cat lives, according to quantum mechanics. Until the box is opened and a measurement is made, the atom exists in a superposition of decayed and undecayed states. This means, bizarrely, that the cat inside the box is simultaneously both dead and alive. Only when an observer opens the box does the wave function collapse, and the cat assumes a definite state, either dead or alive. The paradox quietly asks, is the act of observation, of consciousness itself, somehow fundamental to shaping reality, or is there a physical process we simply don't understand? Many thoughtful interpretations and proposed solutions have been gently put forward to address the measurement problem, each offering a different way to view the puzzling behavior of the quantum world. One of the most famous is the Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg. This interpretation simply accepts that the wave function collapse is an inherent, unexplainable part of quantum mechanics. It says that the act of measurement fundamentally changes the system, forcing it to pick a single reality. It suggests that reality itself is not fixed until it is observed, a concept that can feel deeply unsettling to our classical intuition. This interpretation essentially states, don't ask too many questions about what happens between observations. Just accept that it works. Another prominent interpretation, the many worlds interpretation MWI, which we touched upon with the grandfather paradox, offers a more radical solution. It suggests that there is no wave function collapse at all. Instead, every time a measurement is made, or every time a quantum possibility is realized, the universe splits into multiple parallel universes, one for each possible outcome. In the case of Schrödinger's cat, when the box is opened, the universe simply branches into two in one universe. The cat is dead, and in another, the cat is alive. There is no collapse. All possibilities are realized in separate realities. This interpretation removes the mysterious act of collapse but introduces an infinitely branching multiverse, a concept that whispers of a reality far vaster and more intricate than we usually imagine. A third category of solutions involves objective collapse theories. These theories propose that the wave function collapses spontaneously, without the need for an observer, perhaps triggered by some objective physical process that we don't yet understand. It suggests that gravity, or some other fundamental force, might play a role in causing the collapse when systems reach a certain size or complexity. These theories attempt to make quantum mechanics more realistic by removing the observer from the equation, ensuring that physical processes occur independently of consciousness. The measurement problem remains a quiet, profound puzzle at the heart of quantum mechanics, a persistent whisper of the strange and wonderful nature of reality. It challenges us to rethink our most basic assumptions about what it means to exist and how information is recorded and perceived in the universe. It's a testament to the fact that even in our most successful scientific theories, there are still deep, philosophical questions that quietly invite us to explore further. Let's now gently turn our thoughts to the string theory landscape paradox. This is a fascinating and somewhat daunting paradox that arises from the vast, almost incomprehensible number of possible universes predicted by string theory. Imagine, for a moment, not just one universe, but an infinite, mind-boggling array of possibilities, each with its own unique set of physical laws and properties. String theory, a leading candidate for a unified theory of everything, suggests that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating one-dimensional strings. Different vibration modes of these strings give rise to different particles and forces. The paradox emerges when we realize that string theory doesn't uniquely predict a single universe like our own. Instead, it allows for an incredibly vast number of possible vacuum states, each corresponding to a different set of fundamental constants. particle masses, and even the number of dimensions of spacetime. This enormous collection of possible universes is referred to as the string theory landscape. Imagine a landscape of mountains and valleys, where each peak and trough represents a different universe with unique physical laws. The estimated number of these possible universes is astronomical, often quoted as 10,500 or even higher, a number so colossal that it truly transcends our ability to grasp it. The paradox, then, is this: if string theory allows for such a vast multitude of universes, each with potentially different laws, why do we find ourselves in this particular universe, with its very specific and finely tuned physical constants that allow for the existence of stars, galaxies, and life itself? Why is our universe so uniquely suited for us? It's a quiet challenge to the idea of predictive power in string theory, whispering that it might predict too much, rather than too little, if string theory can describe virtually any universe. What does it tell us about our universe? This challenge has led to much quiet contemplation and several proposed ways to understand it. One of the most prominent is the anthropic principle, which we touched upon earlier, in the context of the string theory landscape. The anthropic principle suggests that we exist in this particular universe because it is one of the very few in the vast landscape that can support life. Imagine trying to find a habitable island in an ocean filled with countless islands, most of them barren or hostile. We are simply observing the universe that allows for our existence. This doesn't mean our universe is special in a divine sense, but rather that our presence as observers biases our perception towards universes where observers are possible. It's a subtle shift in perspective, from trying to explain why the universe is this way to understanding why we are here to observe it being this way. Another proposed solution involves the idea of cosmic inflation. Combined with the landscape concept, imagine that cosmic inflation, the rapid expansion in the early universe, didn't just happen once, but constantly, eternally, creating an endless multitude of pocket universes within a larger, ever-expanding multiverse. Each of these pocket universes could then settle into a different vacuum state from the string theory landscape, resulting in a true multiverse with varying physical laws. Our universe would simply be one such pocket. This idea, called eternal inflation, would naturally populate the entire landscape of possibilities, making the existence of our particular finely tuned universe simply a statistical inevitability within an infinite ensemble. It's a grand, sweeping vision, offering a quiet resolution by expanding the very definition of universe. Some physicists are also working on finding dynamic mechanisms within string theory itself that might favor the selection of certain vacuum states over others. Perhaps there are deeper principles, subtle cosmic pressures, that guide the universe towards a specific set of laws, making our universe not just a random draw from the landscape, but a preferred outcome. This would be a more deterministic approach, suggesting that our universe is not just lucky, but is the natural consequence of some underlying yet undiscovered rule. The string theory landscape paradox remains a frontier of modern physics, a quiet, profound question that invites us to ponder the very nature of existence and the role of fundamental theories. It challenges us to reconcile the incredible predictive power of string theory with the vastness of its own implications, pushing us to explore new ways of thinking about reality and our place within it. It's a beautiful testament to the ongoing journey of human inquiry, where answers often lead to even deeper, more fascinating questions. Now, let's gently consider the information loss paradox in quantum gravity. This paradox, deeply intertwined with the black hole information paradox we discussed earlier, extends the problem to the realm where quantum mechanics and general relativity are both at play, specifically in the extreme conditions near singularities and within the very early universe. Imagine a tiny, impossible point where the rules of the incredibly small meet the rules of the incredibly large, and our understanding begins to fray. The core of this paradox arises from the fundamental conflict between the principle of information conservation in quantum mechanics and the behavior of gravity as described by general relativity, particularly in the context of gravitational collapse and the formation of black holes. As we've softly explored, quantum mechanics asserts that information about the state of a system can never be truly lost. It might be scrambled or hidden, but it always exists somewhere. However, when matter collapses to form a black hole, and then that black hole potentially evaporates via Hawking radiation, it seems that all the information about the original matter is simply gone, seemingly forever. This is where quantum gravity steps in, or rather, where its absence deepens the mystery. We don't yet have a complete, unified theory of quantum gravity, a theory that can seamlessly describe both the quantum world and the gravitational force. This lack of a unified theory is precisely why the information loss paradox persists. Our current theories are like two beautiful, but separate, languages attempting to describe the same profound cosmic event, and they often lead to contradictory conclusions. Without a complete theory of quantum gravity, we cannot definitively say what happens to information in the extreme gravitational environments of black holes, or at the very beginning of the universe, the paradox. Then is a quiet, insistent whisper that our understanding of reality is incomplete. It implies that either quantum mechanics or general relativity, or perhaps both, need to be fundamentally revised or united in a new, elegant framework. It's a call for a deeper, more harmonious language to describe the cosmos. Many solutions have been gently proposed, each offering a different path toward resolving this profound dilemma. One major line of inquiry involves the idea that information is indeed preserved, perhaps at the event horizon itself. Theories like the holographic principle suggest that all the information contained within a volume of space, like the interior of a black hole, can be fully described by data on its two-dimensional boundary. The event horizon. Imagine the event horizon as a giant cosmic screen, subtly encoding every detail of what lies within. If information is stored on the surface of the event horizon, then perhaps it can be carried away by Hawking radiation, but in a way that is incredibly complex and requires a full theory of quantum gravity to decode. This would mean information is scrambled, not lost. Another fascinating possibility. Often explored in the context of loop quantum gravity, a contender for quantum gravity theory, is that space-time itself might not be smooth and continuous, but instead quantized into tiny, discrete loops or atoms of space. In this view, black hole singularities might not be true infinities, but rather regions where space-time becomes incredibly compressed and distorted, potentially allowing information to bounce off a singularity and reemerge. Perhaps in a different form, this would fundamentally alter our understanding of what happens at the heart of a black hole, making it less of an information black hole and more of an information scrambler with an exit. A more radical idea is that the information might pass into a baby universe that buds off from our own. Imagine a black hole as a portal, not to destruction, but to the creation of a new, separate reality. This concept, while highly speculative, offers a way for information to be preserved by moving it into a different cosmic domain, bypassing the apparent loss in our universe. The information loss paradox in quantum gravity remains one of the most challenging and deeply investigated problems in theoretical physics. It's a quiet, insistent reminder that despite our incredible progress, there are still profound mysteries at the very edge of our knowledge, where our most cherished theories meet their limits. Resolving this paradox would not only illuminate the inner workings of black holes, but would also provide crucial insights into the ultimate nature of space, time, and information itself. It's a quest for the most fundamental truths, a gentle whisper from the heart of the cosmos. Now, let's gently contemplate the arrow of time paradox. This is a beautiful and deeply philosophical paradox that arises from a fundamental observation. Time in our everyday experience clearly has a direction. It flows relentlessly from the past, through the present, and into the future. We remember the past, we experience the present, and we anticipate the future. We see milk spill and break, but we never see spilled milk gather itself back into a carton. We age, buildings crumble, stars burn out, all processes that illustrate a clear, irreversible progression of time. This is often referred to as the thermodynamic arrow of time, linked directly to the increase of entropy. However, the laws of fundamental physics, the very equations that describe the motion of particles and forces, are almost entirely time-symmetric. This means that if you were to watch a movie of any fundamental physical process, like two particles colliding, and then play that movie in reverse, the reversed process would still be perfectly consistent with the laws of physics. There's nothing in the fundamental equations of motion that specifies a preferred direction for time. If you reverse the film of two billiard balls colliding, it would still look like a perfectly valid physical interaction. So, the paradox is this: if the fundamental laws of the universe don't distinguish between past and future, why does time in our macroscopic experience always seem to move forward? Why is there an arrow of time pointing stubbornly in one direction? It's a quiet, persistent question that challenges our intuition. This apparent discrepancy between the microscopic time symmetry of physical laws and the macroscopic time asymmetry of everyday experience is the arrow of time paradox. It quietly suggests that the flow of time, or at least its perceived directionality, might be an emergent property of the universe, rather than a fundamental one. Several thoughtful solutions and interpretations have been gently proposed to address this paradox. The most widely accepted explanation links the arrow of time directly to the second law of thermodynamics and the concept of entropy, as we've gently discussed. The second law states that the total entropy or disorder of an isolated system always increases over time. The universe, from its highly ordered state at the Big Bang, has been continuously moving towards a state of greater disorder. This increase in entropy provides a clear, irreversible direction for time. For instance, a broken egg has more entropy than an intact one, and we never observe the reverse process spontaneously occurring. So, the thermodynamic arrow of time is simply the direction in which entropy increases. Our memory, our sense of cause and effect, and all irreversible processes are aligned with this direction. However, this still leaves a deeper question: why did the universe begin in such a low entropy, highly ordered state in the first place, if the natural tendency is towards disorder? Why wasn't the Big Bang the most disordered state imaginable? This leads to the idea that the initial conditions of the universe were incredibly unique, a gentle whisper of a finely tuned beginning. Another line of thought, more philosophical, explores the psychological arrow of time. Our brains are structured to remember the past, but not the future. This creates a subjective experience of time moving forward. While this doesn't explain the physical arrow, it highlights how our perception is deeply tied to the thermodynamic arrow. We build memories of past states because those states were lower in entropy than the future states. Some interpretations also consider the cosmological arrow of time, linked to the expansion of the universe. As the universe expands, it moves from a hotter, denser state to a colder, more diffuse one. This expansion provides another directional aspect to time, seemingly aligned with the thermodynamic arrow. However, if the universe eventually contracts in a big crunch scenario, would the arrow of time reverse? This is a fascinating, speculative question. The arrow of time paradox remains a profound area of inquiry, weaving together physics, philosophy, and cosmology. It challenges us to consider whether time is a fundamental river flowing independently, or merely a reflection of the universe's quiet journey from order to disorder. It's a testament to the fact that even the most basic elements of our experience can hold the deepest cosmic mysteries. Let's now gently turn our thoughts to the black hole firewall paradox. This is a relatively newer, yet deeply perplexing paradox in theoretical physics that challenges our understanding of black holes and the very nature of spacetime. It arose from a thoughtful attempt to reconcile the seemingly contradictory principles of quantum mechanics, general relativity, and the black hole information paradox we've already quietly explored. Imagine, for a moment, an unfortunate astronaut, or perhaps just a brave particle, falling into a black hole. According to Einstein's theory of general relativity, which describes gravity, as this object crosses the event horizon, the point of no return, it should experience nothing out of the ordinary locally. The spacetime at the event horizon should be perfectly smooth and unremarkable for the falling object. This is known as the no-drama principle. The falling observer should not feel anything unusual as they cross the event horizon. A gentle, silent passage into the unknown. They would only feel the increasing tidal forces as they approach the central singularity. However, the paradox arises when we try to reconcile this no-drama principle with quantum mechanics and the idea of Hawking radiation. As we've discussed, Hawking radiation suggests that black holes slowly evaporate by emitting particles from their event horizon. These particles are thought to be entangled with particles that fall into the black hole. Quantum entanglement is a bizarre and beautiful phenomenon where two particles are linked in such a way that the state of one instantaneously affects the state of the other. No matter how far apart they are, it's like two silently spinning coins, where if one lands on heads, you instantly know the other is tails, even if they are light years apart. The paradox emerges from the demand that information be conserved and that quantum entanglement is not broken. If a particle that falls into a black hole becomes entangled with a particle that escapes as Hawking radiation, and then the escaping particle also becomes entangled with another particle outside the black hole. A fundamental rule of quantum mechanics called monogamy of entanglement, which states a particle can only be fully entangled with one other particle at a time, is violated. To prevent this violation, some physicists proposed that there must be a firewall at the event horizon, a scorching, energetic region that would destroy anything that falls into it, including the falling particle, breaking its entanglement. So, the paradox is this: if there is a firewall, it violates general relativity's no-drama principle, as the falling object would be violently burned. But if there is no firewall, then quantum mechanics' principle of entanglement or information conservation seems to be violated. It's a quiet, intense battle between our two most successful theories of physics, each seemingly demanding a different reality at the very edge of a black hole. Many theoretical solutions and interpretations have been gently proposed to resolve the black hole firewall paradox, each one attempting to find a harmonious balance between general relativity and quantum mechanics. One approach suggests that perhaps information is not truly lost, but is re-encoded or smeared out across the entire black hole in a way that preserves entanglement. This is often linked to the holographic principle, suggesting that the information is somehow projected onto the event horizon itself. If the information about the falling particle is already on the surface of the black hole, then there's no need for a firewall to destroy it to resolve entanglement. This would mean a more complex, less direct storage of information than we typically imagine. Another proposed solution involves modifying our understanding of quantum entanglement itself in extreme gravitational environments. Perhaps the rules of entanglement change near a black hole, allowing for the apparent violation without requiring a destructive firewall. This would require a significant revision of quantum mechanics under extreme conditions, a quiet whisper that our current understanding might be incomplete. Some physicists also explore the idea that the event horizon itself is a more complex quantum object than we currently perceive. It might not be a sharp, classical boundary, but a fuzzy, quantum mechanical region where space and time become intertwined in ways we don't yet fully grasp. This fuzziness could allow for the smooth passage of information and prevent the formation of a firewall, a more radical solution. and one that often feels like a gentle reimagining of reality, is that the no-drama principle itself might be violated under certain circumstances, or that quantum effects become so dominant at the event horizon that the classical picture of smooth spacetime simply breaks down. This would imply that falling into a black hole is, indeed, a much more dramatic event than general relativity initially predicted, fundamentally altering the experience at the event horizon, the black hole. Firewall paradox remains an active and vibrant area of research in theoretical physics, a quiet, persistent challenge that pushes the boundaries of our knowledge. Resolving it would provide deep insights into the nature of spacetime, the behavior of quantum gravity, and the ultimate fate of information in the universe. It's a testament to the ongoing quest to unify our understanding of the cosmos, to weave together the threads of gravity and quantum mechanics into a single, elegant tapestry. Let's now gently turn our thoughts to the fine-tuning paradox. This is a profound and deeply contemplative paradox that arises from the astonishing observation that the fundamental physical constants and initial conditions of our universe appear to be incredibly, almost impossibly, fine-tuned for the existence of life. Imagine a colossal cosmic dial board with thousands of knobs, each representing a fundamental constant of nature, and each knob has to be set to an incredibly precise value for life, particularly complex life like our own, to exist. The paradox is this: if even one of these constants were slightly different, even by a tiny fraction, the universe as we know it would not exist, and certainly, life would be impossible. For example, consider the strength of the strong nuclear force, which binds protons and neutrons together in atomic nuclei. If it were even slightly weaker, stable atoms heavier than hydrogen wouldn't form, and there would be no chemistry. If it were slightly stronger, hydrogen atoms would fuse too easily, stars would burn out too quickly, and there would be no long-lived stars to support planets. Another example is the mass of the electron compared to the proton. If this ratio were significantly different, chemical bonds might not form in the stable ways necessary for complex molecules. Or think of the cosmological constant, that mysterious force driving the accelerating expansion of the universe. Its observed value is incredibly small, almost zero, yet if it were just a little larger, the universe would have expanded so rapidly that galaxies and stars could never have formed. If it were slightly smaller, the universe might have collapsed back in on itself before life had a chance to evolve. The list of such finely tuned parameters goes on, whispering of a cosmic precision that seems almost miraculous. This extreme sensitivity of the universe to its fundamental parameters, making it appear as if it were precisely designed for life, is the fine-tuning paradox. It quietly asks, is this incredible fine-tuning just an astonishing coincidence? Or does it imply something deeper about the nature of reality, or even our place within it? Many thoughtful solutions and interpretations have been gently proposed to address this profound paradox, each offering a different way to view the universe's apparent cosmic precision. One of the most prevalent is the multiverse hypothesis, which we've quietly encountered before. In this context, the multiverse suggests that our universe is just one of an infinite, or at least astronomically large, number of universes, each with a different set of physical constants and initial conditions. If there are countless universes, then it's no longer surprising that at least one of them, purely by chance, would have the precise conditions necessary for life to emerge. We simply find ourselves in one of these rare, life-permitting universes because we wouldn't exist to observe any others. It's like drawing a winning lottery ticket from an infinite pile of tickets. Someone was bound to win, and it happened to be us. This solution shifts the miracle from a single universe to the vast ensemble of the multiverse. Another perspective is the anthropic principle, which works hand in hand with the multiverse idea. It states that the fundamental constants of the universe must be precisely as they are because if they were otherwise, we would not be here to observe them. It's a form of selection effect we can only ever observe universes compatible with our own existence. This doesn't explain why the constants are what they are in a fundamental sense, but rather why we see them that way. It's a subtle but significant distinction, a quiet acknowledgement of our observational bias. A third, more contentious, approach involves the idea that there might be a deeper, currently unknown theory of everything that fundamentally requires these constants to have precisely the values they do. In this view, the fine-tuning wouldn't be a coincidence or a product of multiple universes, but a necessary consequence of a more fundamental, elegant theory that we haven't yet discovered. This would mean that the universe isn't just lucky, but is instead governed by even more profound and unbreakable rules that inherently lead to the conditions for life. It's a quiet hope that the apparent tuning is actually a necessary outcome of a deeper cosmic harmony. The fine-tuning paradox remains a captivating and deeply debated topic in cosmology and philosophy. It pushes us to contemplate the very nature of existence, the statistical likelihood of our universe, and whether there is something fundamentally unique or merely statistically probable about our cosmic home. It's a quiet whisper that invites us to look beyond mere observation and to ponder the profound implications of what we find. Let's now gently explore the age of the universe. Paradox. This is a paradox that, for a time, posed a quiet, perplexing challenge to our understanding of cosmic history. It arose from the subtle contradiction between the estimated age of the universe, based on its expansion, and the observed ages of some of the oldest stars. Imagine, for a moment, a universe that seems younger than some of the ancient, wise stars quietly burning within it. The age of our universe is primarily determined by observing its expansion rate, through meticulous measurements of distant galaxies and their recession velocities. Astronomers can trace the universe's expansion backward in time, much like rewinding a cosmic film, until it reaches a point of unimaginable density and heat, the Big Bang. This process gives us an estimated age for the universe, often cited as approximately 13.8 billion years. This age is consistent with the cosmic microwave background CMB radiation, which is a faint, ancient echo of the Big Bang itself. However, the paradox emerged when early observations of some of the oldest stars, particularly those found in globular clusters, seemed to suggest that these stars were older than the calculated age of the universe. Globular clusters are dense, spherical collections of millions of stars, often found orbiting the halos of galaxies. Their stars are typically very old, formed early in the universe's history. If these stars were, for example, 15 or 16 billion years old, while the universe was calculated to be only 13.8 billion years old, it presented a fundamental problem. How can a child be older than its parent? It's a quiet, unsettling contradiction that suggested a deep flaw in our understanding of either stellar evolution or cosmology. This seemingly impossible scenario, where parts of the universe appeared older than the universe itself, was the age of the universe paradox. It was a profound challenge that pushed cosmologists and astrophysicists to re-examine their assumptions and refine their measurements. Fortunately, this particular paradox has been largely and gently resolved through decades of painstaking research and advancements in both observational astronomy and theoretical modeling. One of the most significant factors in its resolution was the refinement of the Hubble constant. The Hubble constant is a crucial value that describes the rate at which the universe is expanding. Earlier measurements of this constant had larger uncertainties, leading to a wider range of possible ages for the universe. As measurement techniques improved through technologies like the Hubble Space Telescope and sophisticated methods for measuring distances to faraway galaxies, the value of the Hubble constant became more precise. This led to a more accurate and ultimately older estimate for the age of the universe, pushing it comfortably beyond the age of the oldest observed stars. Another key factor in resolving the paradox was a more accurate understanding of stellar evolution, particularly the life cycles of stars within globular clusters. Astrophysicists developed more refined models of how stars burn their fuel, how long they live, and how their age can be precisely determined by observing their light and composition. These improved models led to slightly younger estimates for the ages of the oldest stars, bringing them into alignment with the refined age of the universe. The new calculations showed that while these stars were indeed ancient, they were consistently younger than the revised age of the cosmos itself. Finally, the discovery and confirmation of dark energy played a crucial role. Dark energy, that mysterious force accelerating the expansion of the universe, means that the universe has been expanding faster in recent cosmic history than it was in its earlier phases. Accounting for this accelerated expansion allowed for an even more accurate and slightly older calculation of the universe's age. It painted a more complete picture of cosmic history, one where the universe had enough time to form its oldest stars and for those stars to evolve without contradiction. The resolution of the age of the universe paradox is a testament to the scientific method when faced with a quiet contradiction. We don't abandon our theories, but rather refine our measurements, improve our models, and seek deeper understanding. It illustrates how apparent paradoxes often lead to profound breakthroughs, quietly pushing the boundaries of human knowledge and offering a more coherent, beautiful picture of our cosmic past. It's a gentle reminder that even the most stubborn mysteries can, with patience and ingenuity, eventually yield to understanding. Let's now gently turn our thoughts to the vacuum catastrophe. This is a profound and unsettling paradox, often considered one of the most significant unsolved problems in theoretical physics. Even more challenging than the vacuum energy paradox we quietly explored earlier. It arises from the staggering discrepancy between the theoretical prediction of vacuum energy and its astronomically small observed value. Specifically in the context of general relativity, imagine, for a moment, the fabric of space-time itself. According to Einstein's theory of general relativity, energy and mass cause space-time to curve, and this curvature is what we perceive as gravity. The theory also implies that even the energy inherent in empty space, the vacuum energy, should exert a gravitational pull and contribute to the curvature of the universe, as we discussed with the vacuum energy paradox. Quantum field theory predicts that empty space is teeming with virtual particles constantly fluctuating into and out of existence, giving rise to an enormous amount of vacuum energy. The theoretical calculation for this energy density is mind-bogglingly large, vastly exceeding the energy density of all matter and radiation in the universe combined. It's an immense, almost infinite number, a cosmic roar that should utterly dominate everything. Now, here's where the catastrophe part of the paradox quietly emerges. If this enormous theoretical vacuum energy actually contributed to gravity, as predicted by general relativity, it would cause the universe to expand at an incredibly, unimaginably rapid rate. The expansion would be so violent, so instantaneous, that matter would never have had the chance to clump together to form atoms. Much less stars, galaxies, or planets. The universe would be a cold, diffuse, empty void, expanding into oblivion almost as soon as it began. Clearly, this is not the universe we observe. Our universe is filled with magnificent structures, quietly expanding at a relatively modest and accelerating rate, a pace that has allowed for billions of years of cosmic evolution and the emergence of life. The vacuum catastrophe is this catastrophic discrepancy. The vacuum energy predicted by quantum field theory is so incredibly vast that if it were truly contributing to gravity in the way general relativity suggests, our universe simply could not exist in its current form. The difference between the theoretically predicted value and the observed cosmological constant, which represents the vacuum energy's contribution to expansion, is a factor of 10⁻⁴, an almost unfathomable gulf. It's a quiet scream in the very equations of physics, indicating a profound misunderstanding at the intersection of quantum mechanics and gravity. This paradox implies that either our understanding of vacuum energy, or our understanding of gravity, or perhaps both, are fundamentally incomplete when it comes to the deep structure of the cosmos. It suggests that there is a missing piece, a silent puzzle that continues to elude the brightest minds. Many thoughtful solutions have been gently proposed to address this most profound of paradoxes, each attempting to bridge the enormous gap between theory and observation. One approach involves the idea of supersymmetry, which we touched upon earlier. Supersymmetry posits that for every known particle, there is a heavier, unseen superpartner. If supersymmetry were perfectly realized, the positive contributions to vacuum energy from ordinary particles would be precisely canceled out by the negative contributions from their superpartners, leading to a vacuum energy of exactly zero. However, since we don't observe supersymmetry at low energies, meaning we haven't found these superpartners in our accelerators, it must be a broken symmetry. The challenge is to explain why this breaking still leaves such a tiny, but non-zero, amount of vacuum energy. It's a quiet search for a cosmic balance point. Another line of thought suggests that there might be a dynamic cancellation mechanism at play, an intricate, self-adjusting process in the universe that somehow naturally suppresses the vacuum energy to its observed tiny value. This would imply a feedback loop, or some as-yet unknown cosmic principle that actively works to keep the vacuum stable and low. It's like an unseen governor on a cosmic engine, quietly regulating its speed. A third, more radical approach is to reconsider the nature of gravity itself at the quantum level. Perhaps general relativity needs to be modified when applied to the quantum vacuum. Some theories of quantum gravity, like loop quantum gravity or string theory, might offer new insights into how vacuum energy interacts with space-time, potentially resolving the catastrophe by reframing the very rules of the game. Finally, the anthropic principle and the multiverse hypothesis are also often invoked, as they were for the fine-tuning paradox. If there are countless universes, each with different vacuum energy values, then we simply happen to reside in one of the extraordinarily rare universes where the vacuum energy is small enough to allow for structure formation and life. This doesn't explain why the vacuum energy is small in our universe in a fundamental sense, but why we observe it to be small. The vacuum catastrophe remains arguably the biggest outstanding problem in fundamental physics. A quiet, persistent whisper that highlights the deep incompatibility between our two most successful theories, quantum mechanics and general relativity. Resolving it would likely require a revolutionary breakthrough, a profound paradigm shift that fundamentally changes our understanding of the universe at its most basic level. It's a testament to the vast, beautiful, and still largely mysterious nature of the cosmos. Let's now gently explore the many worlds interpretation paradox. This is a profound and captivating paradox, deeply rooted in the heart of quantum mechanics. That offers a radical, yet elegant, solution to the measurement problem we've quietly discussed. Imagine, for a moment, that every time a choice is made, every time a quantum possibility is realized, the universe doesn't simply pick one outcome, but subtly splits into countless parallel realities. The many worlds interpretation MWI, first proposed by Hugh Everett III in 1957, suggests that the wave function, which describes all possible states of a quantum system, never actually collapses. Instead, when a quantum measurement is made, or when any interaction occurs that could lead to different outcomes, the universe itself branches into a multitude of parallel universes. In each of these newly formed universes, one of the possible outcomes of that measurement or interaction becomes a reality. The paradox, or rather the profound implication, is that this interpretation implies an almost unimaginably vast and ever-expanding multiverse. Every time you make a decision to turn left or right, to pick up a book or not, the universe might be splitting into new realities where you made the other choice. Every single quantum event, from the decay of a radioactive atom to the subtle flicker of a photon, leads to a branching of reality. This means that every single possibility, no matter how remote, is actually realized in some parallel universe. It's a concept that stretches our minds to their very limits, suggesting a reality far grander and more intricate than our immediate experience suggests. The MWI was originally developed to resolve the measurement problem in quantum mechanics without invoking the mysterious collapse of the wave function, which is not described by the equations of quantum mechanics themselves. In the MWI, there is no need for a conscious observer to cause the collapse. All possible outcomes simply exist in their own separate, yet equally real branches of reality. It's a deterministic view, where randomness is merely a consequence of our inability to perceive all existing branches. This interpretation elegantly resolves many quantum paradoxes. Like Schrödinger's cat, in the many worlds interpretation, when the box is opened, the universe simply splits into two branches in one branch. The observer sees a live cat, and in another parallel branch, the observer sees a dead cat. Both outcomes are equally real, existing in their own distinct realities. There's no superposition of dead and alive cats. There are simply two separate cats, one living and one dead, in different universes. This avoids the philosophical awkwardness of a single reality being somehow dependent on observation. However, despite its elegant solutions to some quantum puzzles, the many worlds interpretation itself presents its own set of philosophical and practical challenges, which some might consider its own paradoxes. One of the most significant is the unfathomable number of parallel universes it implies. If every quantum interaction, no matter how tiny, leads to a split, the number of universes would grow exponentially, becoming truly infinite. This raises questions about the testability of the MWI if these other universes are inherently unobservable. How can we ever verify their existence? It's a quiet whisper about the limits of scientific inquiry. Another challenge is the concept of probability. If every outcome happens in some universe, what does it mean to say that an event has a certain probability of occurring? If you toss a coin, and it lands both heads in one universe and tails in another, where does the 50-50 probability come from? Proponents of MWI argue that probability emerges from the perspective of an observer within a single branch. But this remains a complex area of debate. The many worlds interpretation is a radical and powerful interpretation of quantum mechanics. A quiet invitation to rethink the very nature of reality. It proposes that the universe is not just the single reality we perceive, but an endlessly branching tree of possibilities, where every potential outcome is realized somewhere. While it elegantly resolves some of the deepest mysteries of the quantum world, it simultaneously opens up new, profound questions about existence, probability, and the very fabric of our cosmos. It's a testament to the enduring power of human curiosity, gently pushing the boundaries of what we thought was possible. Let's now gently turn our thoughts to the holographic principle paradox. This is a profound and deeply counterintuitive concept that stems from the physics of black holes and string theory. Imagine, for a moment, that the three-dimensional reality we experience, with all its depth, complexity, and seemingly solid objects, might actually be a projection from a much simpler, two-dimensional surface, and it's like watching a 3D movie, but realizing that all the information for that movie is actually encoded on a flat screen. The holographic principle states that all the information contained in a specific region of space, particularly the information describing its gravitational content, can be completely encoded on a two-dimensional boundary surface of that region. This idea first emerged from the study of black holes. When something falls into a black hole, all its information, seemingly, should vanish. However, as we've discussed, quantum mechanics demands that information is never truly lost. Physicists like Jacob Bekenstein and Stephen Hawking showed that black holes have an entropy, and this entropy is proportional not to their volume, but to the area of their event horizon. This was a revolutionary insight. It implied that the information content of a black hole, which supposedly contains all the quantum data of everything that ever fell into it, is encoded on its surface, not its interior, the paradox. Then, arises from extending this idea beyond black holes to the entire universe. If the information of a 3D black hole can be encoded on its 2D boundary, could our entire 3D universe similarly be a holographic projection from a distant 2D boundary? This is where the concept becomes truly mind-bending. It suggests that what we perceive as three spatial dimensions might actually be an illusion, and that the fundamental reality exists on a lower dimensional surface or screen at the edge of our universe. This idea challenges our most basic understanding of reality and space. If it's true, it would mean that all the information about every particle, every star, every galaxy, and indeed, ourselves, is somehow encoded on a distant, flat cosmic boundary. It's a quiet whisper that the universe might be a grand, intricate illusion. Many thoughtful solutions and interpretations have been gently proposed to address this profound principle, or to explore its implications. One of the most significant pieces of evidence and a crucial step in understanding the holographic principle came from the anti-de Sitter conformal field theory AD-S-CFT correspondence. This is a theoretical duality, a profound mathematical equivalence between a specific type of gravitational theory in a certain number of dimensions, anti-de Sitter space, which is a negatively curved spacetime, and a quantum field theory with no gravity in one fewer dimension, a conformal field theory. The ADS-CFT correspondence acts like a cosmic dictionary, showing that these two seemingly very different types of theories are actually two different ways of describing the exact same physics. What happens in the 3D or higher gravitational bulk of anti-de Sitter space can be perfectly translated into events happening on its 2D or lower boundary, which is the domain of the conformal field theory. This mathematical proof, though specific to certain types of universes not exactly our own, which is approximately flat, not negatively curved, provides a powerful theoretical framework for how a holographic universe could actually work. It demonstrates that a lower dimensional theory can indeed encode all the information of a higher dimensional gravitational theory. The implications of the holographic principle are vast and deeply philosophical. If our universe is indeed a hologram, it could provide a radical solution to the information paradox in black holes, suggesting that information is never truly lost but is preserved on the event horizon. It could also offer new insights into quantum gravity, as it suggests a fundamental relationship between gravity and quantum field theory. However, extending the AD-S-CFT correspondence to our own universe, which is nearly flat and accelerating, remains a major challenge. The holographic principle is still very much a theoretical concept, a quiet frontier in our quest to understand the deepest nature of reality. It pushes us to consider that what we perceive as solid and real might be far more ephemeral and interconnected than we ever imagined. A gentle invitation to see the universe as an intricate, cosmic projection. Let's now gently turn our thoughts to the principle of locality paradox. This is a deeply fundamental concept in physics, yet one that is subtly challenged by the strange and beautiful world of quantum mechanics. Imagine, for a moment, that everything in the universe only interacts with its immediate surroundings. A billiard ball only moves when another ball hits it. Or if it's pushed by a cue, an event in one place should only affect another place if some influence, like a force or a particle, travels between them. This is the essence of locality. Influences propagate no faster than the speed of light, and objects are only affected by their immediate environment. The principle of locality is a cornerstone of both classical physics and Einstein's theory of special relativity. It means that there are no spooky actions at a distance, no instantaneous influences that can cross vast stretches of space without anything physically traveling. If you cause something to happen on Earth, its effect won't be felt on a distant star until light or some other signal has had time to travel there. This makes intuitive sense to us. It underpins our everyday understanding of cause and effect. However, the paradox quietly emerges from the astonishing phenomenon of quantum entanglement. As we've gently discussed, quantum entanglement is a peculiar and profound connection between two or more particles, where their fates are intertwined in such a way that the state of one particle instantly influences the state of the other. No matter how far apart they are, imagine two quantum dice. Separated by light years, if you roll one and it lands on a 3, the other, instantly and without any apparent communication, also lands on a 3. This spooky action at a distance, as Einstein famously called it, seems to directly contradict the principle of locality. If measuring one entangled particle instantaneously determines the state of its distant partner, then it appears that information, or at least some kind of influence, is traveling faster than the speed of light, seemingly violating the speed limit of the universe set by special relativity. This is the quiet heart of the principle of locality paradox. How can entangled particles exhibit such instantaneous correlations without violating the fundamental principle that information cannot travel faster than light? Many thoughtful solutions and interpretations have been gently proposed to address this profound paradox. One of the most popular is the Copenhagen interpretation of quantum mechanics, which, as we recall, simply states that the wave function collapses upon measurement. In this view, the entanglement doesn't involve any action or communication between the particles after they are separated. Instead, the particles simply exist in an indeterminate, correlated state until one is measured. The measurement forces one particle to pick a state, and because they are correlated, the other particle's state is then instantly known, even though no information has traveled between them. It's like a pair of gloves, one left and one right, sent to different galaxies. When you open your box and see a left glove, you instantly know the other box contains a right glove, but no information needed to travel between the boxes at superluminal speed to achieve that knowledge. The correlation was established when they were together. Another powerful and more radical solution is the many worlds interpretation, MWI, which we've gently explored. In MWI, there is no wave function collapse instead, when a measurement is made on one entangled particle. The universe splits into multiple parallel universes, with each branch representing a different possible outcome. In each of these branches, the particles are found to be in a definite, correlated state. Since all possible outcomes are realized in different universes, there's no communication needed between particles across vast distances. Everything that could happen, happens, and the correlation is preserved across the branching realities. It's a way of preserving locality by expanding the very definition of reality. A different approach, explored in some hidden variable theories, suggests that quantum mechanics is not a complete theory, and there are underlying unseen, hidden variables that determine the outcomes of measurements, thus preserving locality. However, Bell's theorem and subsequent experimental tests have largely ruled out local hidden variable theories, showing that the correlations observed in entangled systems cannot be explained by any pre-existing localized properties of the particles. This implies that if hidden variables exist, they must be non-local, meaning they would involve some kind of instantaneous influence across space. Which brings us back to the core of the paradox. The principle of locality paradox remains one of the most intellectually stimulating and experimentally confirmed aspects of quantum mechanics. It challenges our classical intuition about how the universe works and hints at a deeper, more interconnected reality than we usually perceive. While it doesn't necessarily mean that information can travel faster than light, it certainly points to a profound non-locality in the quantum world. A quiet whisper that the universe is far stranger and more subtle than we once imagined. It's a testament to the ongoing quest to reconcile our understanding of the small, strange quantum realm with the large, seemingly predictable world we inhabit. Let's now gently turn our thoughts to the observer problem paradox. This is a deeply philosophical and profound paradox that arises directly from the heart of quantum mechanics. Closely related to the measurement problem we've already quietly explored, imagine, for a moment, that the very act of looking at something, of observing it, fundamentally changes its nature. It's as if the universe is holding its breath until you cast your gaze upon it. The paradox states that in quantum mechanics, particles and systems exist in a superposition of all possible states simultaneously until they are observed or measured. It's like a wave of possibilities. However, the moment a measurement or observation occurs, the wave function collapses, and the particle chooses one definite state out of all the possibilities. The problem, the quiet, persistent question, is what precisely constitutes an observer or a measurement? Is it the interaction with a detector? Is it a human consciousness? Does a cat count as an observer? And why does this act of observation seem to play such a fundamental role in shaping reality? This ambiguity around the definition of an observer and the mechanism of wave function collapse is the observer problem paradox. It suggests that consciousness, or at least the act of gaining information, might be inextricably linked to the physical reality we perceive, which feels deeply counterintuitive to our classical understanding of an objective, independent universe. It's a quiet whisper that our role in the cosmos might be far more active than we ever imagined. Many thoughtful solutions and interpretations have been gently proposed to address this profound paradox, each offering a different way to view the puzzling role of observation in the quantum world. One of the most famous is the Copenhagen interpretation, which, as we recall, simply accepts the wave function collapse as a fundamental, unexplained postulate of quantum mechanics. It states that an observation is simply any interaction that causes the quantum system to settle into a definite state. This interpretation often implies that the act of observation by a conscious being is what forces the collapse, though not necessarily, as it could be the interaction with a classical measuring device. It's a pragmatic approach that says, don't ask too many questions about how it collapses, just accept that it does. Another powerful and arguably more elegant solution is the many worlds interpretation MWI, which we've gently discussed in detail. In MWI, there is no actual wave function collapse instead. Every time an observation or interaction occurs, the universe splits into multiple parallel universes, with each branch representing a different possible outcome. In this view, the observer doesn't cause the collapse. Rather, the observer becomes entangled with the observed system, and both the observer and the system evolve into a superposition of different states across different branches. So, in one universe, you observe the cat alive, and in another, you observe it dead. All possibilities are realized, and no collapse needs to happen, thus removing the paradox by removing the collapse itself. This means that the observer is just another part of the quantum system evolving in a larger multiverse. A third category of solutions involves objective collapse theories. These theories propose that wave function collapse is not dependent on a conscious observer, but is a spontaneous physical process that occurs under certain conditions. For example, some theories suggest that collapse is triggered when quantum systems reach a certain size, mass, or complexity, or perhaps due to subtle interactions with gravity. In these theories, the measurement process itself, regardless of whether a conscious being is involved, causes the collapse. This moves the observer out of the picture and makes collapse an objective, physical event. It's a quiet attempt to restore an objective reality to the quantum world. The observer problem. Paradox remains one of the deepest and most debated philosophical questions in quantum mechanics. It forces us to confront the very nature of reality, the role of consciousness, if any, in shaping the physical world, and the relationship between the quantum realm and our macroscopic experience. It's a quiet whisper that invites us to look beyond the surface of what we see and to ponder the profound interconnectedness of existence. It is a testament to the fact that even our most successful scientific theories can still harbor mysteries that transcend mere equations and delve into the very essence of what it means to exist. Let's now gently explore the liar paradox. This is a classic and deeply intriguing paradox, not rooted in the physical universe, but in the very fabric of language, logic, and self-reference. Imagine a statement that, by its very nature, undermines its own truth or falsehood. The simplest and most famous form of the liar paradox is the statement, "This statement is false." Now, let's gently try to determine its truth value. If the statement is true, then, according to what it says, it must be false. This creates a contradiction. If the statement is false, then because it claims to be false, it must actually be true. This also creates a contradiction. This circular logic, where the statement's truth depends on its falsehood and vice versa, means it can be neither true nor false without leading to a logical inconsistency. It's a quiet whisper that reveals a fundamental flaw or limitation in our ordinary understanding of truth and logical reasoning when self-reference is involved. The liar paradox highlights the tricky nature of language and its ability to create self-referential loops that break standard rules of logic. While seemingly simple, the liar paradox has profound implications for logic, philosophy, and even computer science. It suggests that not all grammatically well-formed sentences can be assigned a definite truth value, and it has led to various attempts to redefine or restrict the concept of truth itself. Many thoughtful solutions and approaches have been gently proposed to address this enduring paradox. One common strategy is to restrict self-reference. This approach argues that statements cannot refer to their own truth value. If a statement is not allowed to directly claim its own falsehood, the paradox cannot be constructed. This often involves creating a hierarchy of languages or levels of truth, where statements about truth can only be made from a higher level of language. For example, a statement at level 1 can talk about facts, but a statement about the truth of a level 1 statement must exist at level 2, and so on. This prevents the self-referential loop. Another approach focuses on truth value gaps. This solution suggests that certain statements, like the liar paradox, simply have no truth value. They are neither true nor false. They fall into a gap in our system of logic. This is a way of acknowledging the paradox without trying to force it into a true-false dichotomy that it inherently resists. It's a quiet acceptance that some logical constructs just don't fit neatly into our binary system of truth. A more complex solution involves revision theories of truth. These theories propose that truth is not a static property, but is something that can be revised or updated, in the case of the liar paradox. One might start by assuming it's true, quickly arrive at a contradiction, then revise it to false, also arriving at a contradiction, and so on. This continuous revision process suggests that the liar statement never settles on a stable truth value. It's like a gentle, endless oscillation between truth and falsehood, the liar paradox. Despite its apparent simplicity, continues to be a rich area of study. It challenges our fundamental assumptions about logic and language, pushing us to refine our understanding of how we define and apply the concept of truth. It's a quiet whisper that even in the most basic tools of human thought, there can be profound and unsettling complexities. Let's now gently turn our thoughts to the ship of Theseus paradox. This is an ancient philosophical paradox that quietly challenges our understanding of identity, particularly over time. As components are replaced, imagine a magnificent wooden ship, named Theseus, that has sailed on countless voyages, over centuries. As parts of the ship begin to rot or break, they are replaced, one by one, with new, identical pieces of wood. Eventually, every single plank, mast, and nail of the original ship has been replaced. The paradox, then, is the restored ship still the same ship of Theseus? And to complicate it further, Imagine that all the original discarded parts are carefully collected and then reassembled to form a second ship. Now, which of these two ships, if either, is the true ship of Theseus? The one made of all new parts, or the one made of all the original parts? It's a quiet, profound question about what constitutes identity over time and change. This paradox explores the subtle concepts of identity, persistence, and composition. It forces us to consider what makes something itself when its constituent parts change. Is it the material composition? Is it the form or structure? Is it the historical continuity? Many thoughtful solutions and perspectives have been gently proposed to address this enduring paradox, each offering a different way to understand identity. One common approach focuses on material composition. This view would argue that the ship made of all new parts is not the original ship of Theseus, because it lacks any of the original material. The one assembled from the original parts, however, would be the original ship of Theseus, at least in terms of its material identity. This perspective emphasizes the importance of the physical stuff from which an object is made. It's a quiet adherence to the idea that identity is tied to the very atoms and molecules that compose something. Another perspective emphasizes form or structure. This view would argue that the restored ship, the one with all new parts but maintaining the same design and function as the original, is still the ship of Theseus. The identity is preserved by its shape, its arrangement, and its purpose. Even if the materials are different, the ship reassembled from the old parts, while materially identical to the original, might not be considered the true ship of Theseus if it lacks the continuous historical function or official designation of the original. This is like arguing that a rebuilt house is still the same house if its blueprint remains identical. A third, often more intuitive, solution focuses on historical continuity or narrative identity. This approach suggests that the identity of the ship of Theseus is maintained through its continuous existence and its historical lineage, as long as the replacements are gradual and the ship maintains its function and name. It remains the same ship, the ship assembled from the old parts, even if made of the original material. Would be a new ship, a replica, because it lacks that unbroken chain of existence and purpose. This is like recognizing a person as the same individual throughout their life. Even though their cells are constantly replaced, it's a quiet acknowledgement that a story, a history, can define identity. Finally, some solutions propose that there is no single right answer, and that the paradox highlights the limitations of our language and concepts when discussing identity over time. Perhaps there are multiple valid ways to understand sameness, and the paradox arises only when we try to force a single definition onto a complex situation. It's a quiet invitation to embrace ambiguity. The ship of Theseus paradox continues to be a fascinating thought experiment, particularly relevant in modern contexts like digital identity, artificial intelligence, and even biological processes where components are constantly replaced. It's a quiet whisper that asks what really makes you you. As your cells constantly regenerate and your experiences subtly change your mind, it pushes us to ponder the very essence of identity and how it endures, or doesn't. Through the relentless march of time and change, let's now gently explore the paradox of the heap. Sorite's paradox. This is an ancient philosophical paradox that quietly highlights the inherent vagueness in our language and concepts, particularly when dealing with continuous changes. Imagine a single grain of sand. Clearly, one grain of sand does not make a heap. Now, if you add another grain of sand, do you have a heap? Still, no. What if you keep adding grains of sand, one by one? At what exact point does a collection of grains of sand become a heap? The paradox is this: if you start with something that is clearly not a heap, and you add one grain of sand at a time, each addition seemingly too small to change the status, you will eventually arrive at something that everyone would agree is a heap. Yet, there's no clear, non-arbitrary point at which the transition occurs. If removing one grain from a heap still leaves a heap, then logically, you could remove all grains one by one until you have 0 grains. And by that logic, you'd still have a heap, which is absurd. This paradox isn't just about grains of sand. It applies to any concept that involves a gradual transition along a continuum, where there are no clear, sharp boundaries. Think about a tall person. At what precise height does someone become tall? A bald person. How many hairs must a person lose to be considered bald? Old age. At what exact age does someone become old? The paradox of the heap quietly reveals a fundamental tension between our precise logical reasoning and the inherent vagueness of natural language. It suggests that our everyday terms, while perfectly functional in most contexts, break down when pushed to their logical extremes. Many thoughtful solutions and approaches have been gently proposed to address this enduring paradox, each offering a different way to grapple with vagueness. One common approach is to deny the existence of vague predicates. This radical view argues that concepts like heap or tall are not truly vague, rather, our knowledge is simply incomplete. If we had perfect knowledge, there would be a precise number of grains that constitute a heap, even if we don't know what that number is. This approach often leads to highly counterintuitive conclusions, as it forces sharp boundaries where none seem to exist in reality. It's a quiet insistence on precision where precision seems impossible. Another approach introduces fuzzy logic. Unlike traditional true or false binary logic, fuzzy logic allows for degrees of truth. So, a collection of grains isn't simply a heap or not a heap, but might be 0.1 a heap, then 0.2 a heap, and so on, gradually becoming 0.9 a heap, and eventually 1.0 a heap. This acknowledges the continuum and the gradual nature of the change, without forcing a sharp, arbitrary cutoff point. It's a gentle embrace of nuance and gradualism. A third solution involves supervaluationism. This approach suggests that a vague statement, like "this is a heap," is only definitively true if it's true under all possible ways of making the vague term precise. And it's definitively false if it's false under all such precisifications. If a statement is true in some precise definitions but false in others, as is the case with the marginal cases in the heap paradox, then the statement is neither true nor false. It has a truth-value gap. This is similar to the truth-value gaps we discussed with the liar paradox, suggesting that some statements simply lack a definitive truth assignment due to vagueness. It's a quiet acknowledgement of the limits of definitive truth. Finally, some philosophers argue that the paradox points to the fact that vagueness is an inherent and useful feature of natural language, not a flaw. We use vague terms precisely because they allow for flexibility and approximation, which is highly efficient for communication in most everyday situations. The paradox only arises when we try to apply overly rigid logical standards to terms that were never designed for such precision. It's a quiet celebration of language's adaptive nature. The paradox of the heap continues to be a rich area of study in philosophy of language, logic, and even artificial intelligence. Where creating systems that can handle human language effectively requires grappling with vagueness, it's a quiet whisper that even the simplest words can hide profound logical challenges, pushing us to refine our understanding of how language shapes our perception of the world. Let's now gently turn our thoughts to the teletransportation paradox. This is a modern philosophical paradox that quietly challenges our understanding of personal identity, particularly in the face of radical technological advancements that might allow for instantaneous travel. Imagine a futuristic teletransporter machine. When you step into it, the machine scans your entire body, records every atom and quantum state, and then instantaneously dissolves your original body. This information is then beamed to a distant location, where a new machine assembles an identical copy of you, atom by atom, from raw materials. The paradox. Then, is the person who steps out of the teletransporter at the destination genuinely you, if the original you is destroyed? and a perfect replica is created. Is that replica truly the same individual? What if the original you isn't destroyed, but merely duplicated? Which one is the real you? This thought experiment forces us to confront fundamental questions about what constitutes personal identity. Is it purely physical continuity? The same body? Is it psychological continuity? The same memories? Consciousness? Personality? Or is it something else entirely? This paradox is particularly relevant in the age of advanced technology, as it touches upon concepts like digital consciousness, mind uploading, and the very definition of self in a technologically advanced future. Many thoughtful solutions and perspectives have been gently proposed to address this profound paradox. One common approach emphasizes physical continuity. This view would argue that the person stepping out of the teletransporter is not the original you because there is a break in physical continuity. The original body was destroyed. The replica, no matter how perfect, is just that, a copy, a new person, albeit one with all your memories. This perspective highlights the importance of having the same physical organism persist through time. It's a quiet insistence that identity is irrevocably tied to the specific atoms that make up your body. Another perspective emphasizes psychological continuity. This view would argue that the person stepping out of the teletransporter is the original you because they possess all your memories, beliefs, personality traits, and consciousness. As long as the mental stream of experience is continuous from one moment to the next, even if transferred, then personal identity is preserved. This is often linked to the idea that what makes us us is primarily our mind and experiences. Not the specific physical vessel, it's a gentle focus on the internal world of consciousness. A third, more nuanced solution involves branching identities. This approach suggests that in scenarios where duplication occurs, e.g., if the original person isn't destroyed, identity might branch. Both the original and the copy could be considered you in different senses, or perhaps they become distinct individuals from the moment of duplication. This challenges the idea that personal identity must always be a singular, undivided thing. It's a quiet acceptance of a more complex, perhaps multifaceted self, finally. Some philosophers argue that the paradox points to the limitations of our language and concepts of identity when faced with such extreme hypothetical situations. Our everyday understanding of person and identity might not be robust enough to handle the implications of perfect teletransportation or duplication. Perhaps the concept of identity simply doesn't fully apply in such scenarios, or it needs to be redefined. It's a quiet invitation to rethink our fundamental definitions. The teletransportation paradox continues to be a fascinating thought experiment, particularly as technological advancements push the boundaries of what is possible. It's a quiet whisper that asks if every part of you could be replaced, or even copied. What would truly remain of you? It pushes us to ponder the very essence of what makes an individual unique and how that sense of self persists, or doesn't, through radical change. Let's now gently turn our thoughts to the Achilles and the tortoise paradox. This is one of Zeno's paradoxes, an ancient philosophical problem that subtly challenges our intuitive understanding of motion, space, and time. Imagine a race between the swift hero Achilles and a slow tortoise. The paradox states that if the tortoise is given a head start, Achilles will never be able to catch it. Here's the quiet, perplexing logic. To catch the tortoise, Achilles must first reach the point where the tortoise started. By the time Achilles reaches that point, the tortoise will have moved a little further. Achilles must then reach that new point where the tortoise has moved. But by the time Achilles reaches that point, the tortoise will have moved yet again, a tiny bit further. This process repeats infinitely. There will always be a tiny, ever-diminishing distance for Achilles to cover before he reaches the tortoise's previous position. Because there are an infinite number of these sub-distances, Zeno argued, Achilles would have to complete an infinite number of tasks in a finite amount of time, which he deemed impossible. Therefore, Achilles can never actually catch the tortoise. This paradox isn't about physics in the modern sense. It's a philosophical challenge to the very concept of continuous motion and the divisibility of space and time into infinite smaller parts. It suggests a fundamental problem with how we intuitively grasp the idea of motion. Many thoughtful solutions and approaches have been gently proposed to address this enduring paradox. Often dating back to ancient Greek philosophers and refined by modern mathematics, one of the most powerful resolutions comes from the mathematical concept of infinite series. While Achilles does indeed have to cover an infinite number of ever smaller distances, the sum of those infinite distances can converge to a finite value. Imagine the series 1 to 2 plus 4 plus or 8 plus 1 to 16 plus. This is an infinite series, but its sum is actually 1. Similarly, the infinite series of distances Achilles needs to cover e.g. 10 members, 0.1 members, will add up to a finite distance, which Achilles can cover in a finite amount of time. Modern calculus, developed much later than Zeno, provides the tools to precisely calculate these sums. It's a quiet demonstration that infinite tasks can, mathematically, be completed within finite limits. Another approach focuses on the nature of space and time being continuous. If space and time are truly continuous, then motion is also continuous. The paradox arises from treating motion as a series of discrete, static steps rather than a smooth, unbroken flow. In reality, Achilles doesn't stop at each point where the tortoise was, he moves continuously. Zeno's paradox essentially reifies points in space and moments in time, treating them as obstacles that must be individually overcome, rather than parts of a fluid continuum. Some interpretations also point to the fact that velocity is a rate, a relationship between distance and time. Achilles' velocity is greater than the tortoise's. Therefore, over any given period of time, Achilles covers more distance than the tortoise. This simple fact ensures that the gap between them will always decrease until Achilles overtakes. The paradox is an illusion created by focusing on the diminishing gaps rather than the continuous rates. The Achilles and the tortoise paradox, despite its ancient origins, continues to be a valuable tool for teaching about the complexities of infinity, continuity, and the limitations of intuitive reasoning when faced with deep mathematical and philosophical concepts. It's a quiet whisper that reminds us that even the simplest observations about motion can hide profound logical challenges, pushing us to refine our understanding of the universe's most fundamental properties. Let's now gently turn our thoughts to the paradox of choice. This is a more modern paradox, deeply rooted in psychology and economics, that quietly challenges our common intuition that having more choices is always better. Imagine going to a store to buy jam. You see two options, a simple decision. Now imagine going to another store and being presented with 50 different kinds of jam. You might think this is wonderful, offering you maximum freedom and the best chance to find exactly what you want. However, the paradox is this. While we intuitively believe that more choice leads to greater satisfaction and better outcomes, extensive research suggests that too many choices can actually lead to increased anxiety, decision paralysis, and lower satisfaction. When faced with an overwhelming number of options, people often experience decision paralysis. Instead of making a choice, individuals become overwhelmed by the sheer volume of options and the difficulty of evaluating them, leading to no decision at all. It's a quiet freezing up in the face of abundance. Lower satisfaction with the chosen option. Even if a choice is made, the individual might feel less satisfied with it because they are constantly wondering if they made the best choice, or if a better option existed among the multitude they ignored. This leads to what's called buyer's remorse or regret, increased regret and self-blame. If a poor choice is made, it's easier to blame oneself when there were so many other options available. Rather than blaming external factors, opportunity cost. Evaluating many options means constantly considering what you're not choosing. The perceived value of the unchosen options, the opportunity cost, can detract from the satisfaction derived from the chosen one. The paradox of choice suggests that beyond a certain point, more choices become detrimental to our well-being and decision-making process. It's a quiet whisper that freedom, when taken to extremes, can become a burden. Many thoughtful solutions and strategies have been gently proposed to address this paradox, particularly in fields like marketing, design, and personal productivity. One key solution for individuals is to limit the number of choices they consider. This means setting boundaries, prioritizing what truly matters, and not obsessing over finding the absolute best option. Often, good enough is perfectly sufficient and leads to greater satisfaction. It's a quiet act of self-discipline in a world of endless possibilities. Another strategy is to satisfy rather than maximize. A maximizer is someone who tries to find the absolute best option, no matter how much effort it takes. A satisficer is someone who looks for an option that meets their criteria and then stops searching. Even if there might be a theoretically better one out there, research shows that satisficers tend to be happier and less anxious. It's a gentle embrace of imperfection for designers and marketers. The solution involves curation and simplification instead of overwhelming consumers with every possible option. Present a limited, curated set of choices that are well-defined and clearly differentiated. This reduces cognitive load and makes the decision-making process much smoother and more enjoyable. Think of a restaurant menu with a few signature dishes versus one with hundreds of items. The paradox of choice is not just a philosophical curiosity. It has real-world implications for how we design products, present information, and even approach our personal lives. It's a quiet whisper that reminds us that sometimes less is indeed more, and that true freedom might lie not in limitless options, but in the wisdom of knowing what to choose and what to ignore. It encourages us to find a harmonious balance between choice and well-being. Let's now gently explore the paradox of tolerance. This is a profound and deeply relevant philosophical paradox, particularly in discussions about open societies and free speech. Imagine a society that prides itself on being completely tolerant, accepting all viewpoints and behaviors without judgment. At first glance, this seems like an ideal. However, the paradox, famously articulated by philosopher Karl Popper, is this unlimited tolerance must lead to the disappearance of tolerance. If a society is infinitely tolerant, it must tolerate even the intolerant. If it tolerates those who actively seek to destroy tolerance itself, e.g., groups advocating for tyranny, oppression, or violence against specific groups, then eventually, the tolerant society will be overcome by the intolerant, and tolerance itself will cease to exist. In short, to maintain a tolerant society, one must be intolerant of intolerance. It's a quiet, sobering realization that boundless openness can lead to its own demise. This paradox highlights a critical tension between the ideals of absolute freedom and the necessity of safeguarding the very principles that allow for that freedom. It suggests that there must be limits to tolerance to preserve a tolerant society. Many thoughtful solutions and approaches have been gently proposed to address this enduring paradox, each offering a different way to define the boundaries of tolerance. One common interpretation, directly from Popper, is that tolerance should extend to all who are willing to reciprocate tolerance. However, it is not necessary to tolerate those who refuse to reciprocate. This means that a tolerant society has a right, and perhaps a duty, to defend itself against those who actively seek to undermine its tolerant nature. This might involve restricting the speech or actions of intolerant groups if those actions directly threaten the existence of the tolerant society. It's a quiet call for self-preservation, ensuring that the very foundation of an open society remains intact. Another approach emphasizes the distinction between ideas and actions. A truly tolerant society might tolerate a wide range of even offensive or intolerant ideas, allowing them to be debated and critiqued in the marketplace of ideas. However, when those ideas translate into actions that directly harm or threaten others, or incite violence and discrimination, then the society has a right to intervene and restrict those actions. This draws a line at behavior that infringes upon the rights and safety of others. It's a gentle balance between intellectual freedom and social responsibility. Some solutions also focus on the role of education and dialogue. A tolerant society should actively promote critical thinking, empathy, and an understanding of the value of tolerance. By fostering these values, it aims to reduce the appeal of intolerant ideologies, rather than simply suppressing them. This is a proactive approach, building resilience against intolerance from within. It's a quiet hope that understanding and education can be powerful antidotes. The paradox of tolerance is not merely a theoretical exercise. It has real-world implications for how societies balance free speech with the need to protect vulnerable groups, how democracies handle extremist movements, and how we foster inclusive environments. It's a quiet whisper that reminds us that tolerance is not passive indifference, but an active commitment that sometimes requires difficult choices to defend its own existence. It compels us to define the limits of our openness to preserve the very openness we cherish. Let's now gently turn our thoughts to Russell's paradox. This is a famous paradox in set theory, discovered by the British philosopher and mathematician Bertrand Russell in 1901. It quietly revealed a fundamental flaw in the then prevailing intuitive understanding of set theory, threatening to undermine the very foundations of mathematics. Imagine, for a moment, trying to classify collections of things based on whether they contain themselves. The paradox arises when we consider the concept of a set of all sets that do not contain themselves. Let's call this special set R. So, R, all sets S, such that S. Now, let's gently ask the crucial question, does the set R contain itself? If R contains itself, RR, then by its very definition, which states that R contains only sets that do not contain themselves, R must not contain itself, R. This creates a contradiction. If EIR does not contain itself, R, then by its very definition, which states that R contains all sets that do not contain themselves, R must contain itself, RR. This also creates a contradiction. This circular reasoning, where R contains itself if and only if it does not contain itself, means it's logically impossible for such a set to exist under the naive understanding of set theory. It's a quiet shout from the abstract world of mathematics, pointing out a fundamental flaw in the simple idea that any well-defined property can be used to form a set. Russell's paradox demonstrated that naive set theory, which allowed the formation of a set from any definable property, was inconsistent. If such a set were allowed to exist, it would lead to logical contradictions. And if a system of logic can derive a contradiction, it can prove anything, rendering it useless. This was a crisis for the foundations of mathematics at the turn of the 20th century. Many thoughtful solutions have been gently proposed to address this profound paradox, leading to more rigorous and consistent foundations for set theory. The most widely accepted solution is Zermelo-Fraenkel set theory ZF and its extension with the axiom of choice ZFC, which explicitly restricts the ways in which sets can be formed. Instead of allowing sets to be formed from any property, ZFC introduces a specific set of axioms, fundamental truths that govern set creation. Crucially, it includes an axiom of specification or separation, which states that one can only form a set by taking a subset of an already existing set based on a property. This prevents the creation of problematic self-referential sets like R. You can't just create the set of all sets that don't contain themselves out of thin air. It must be a subset of some larger, predefined set, and no such larger set can contain all sets. This quietly plugs the logical hole that Russell discovered. Another approach, less common but also valid, is type theory, developed by Russell himself and Alfred North Whitehead. Type theory assigns a type to every mathematical object, preventing self-reference by ensuring that a set can only contain elements of a lower type. A set of objects of type n cannot, by definition, contain itself, which would be of type n. This effectively prevents the formation of the paradoxical set R. It's a quiet imposition of a hierarchical structure to maintain logical consistency. Russell's paradox, though abstract, had a monumental impact on mathematics. It forced mathematicians to be more precise and rigorous about the fundamental building blocks of their discipline, leading to the development of robust and consistent foundational systems. It's a quiet whisper that even in the most abstract realms of thought, paradoxes can emerge to reveal deeper truths and reshape our understanding.